হ্যাঁ দেবাশিস,
হ্যাঁ বলো।
হ্যাঁ তাহলে তুমি ইয়েকে পাঠককে ইন্ট্রোডিউস করিয়ে দিচ্ছ।
পঙ্কজকে হ্যাঁ করি, এখনো তো অনির্বাণ জয়েন করলো না।
না না, অনির্বাণকেই বলছি। ও অনির্বাণ এখনো জয়েন করেনি।
না অনির্বাণকে, হ্যাঁ আমি অনির্বাণকে বলে দিচ্ছি, ঠিক আছে। অনির্বাণ তো আগে একবার করেছে, এখনো ঢোকেনি অনির্বাণ, দেখছি।
অনির্বাণের কি কলা পেলাম?
না এখনো ঢোকেনি অনির্বাণ এখনো ঢোকেনি। পঙ্কজ বোধহয়, পঙ্কজ, হ্যালো পঙ্কজ।
Yeah, hello Devashish, how are you?
ওকে, more or less. So how are you?
Yeah, things are okay, as good as they can be during this pandemic, right?
Yes. Okay.
Pankaj,
Oh yeah, hello.
when you are going to organize conferences?
Well, given the current situation, right?
Yeah.
It is almost, I think your conference was also supposed to be online plus offline, right? Hybrid.
No, it's almost
Yes.
online. It's almost online, but some of us like Devashish, Orchon, from Shubro, myself, Priti, we are assembling in a room.
Oh, okay. Yeah, that's good. It gives at least some atmosphere.
Yeah.
Some conferences or some meeting is going on.
Yeah.
Otherwise, it is becoming very, monotonous.
We are telling Shubro to organize one in Bose Institute, I mean offline.
Yeah, it will be good. Actually, it will be good.
Bose Institute has never organized a conference, so I told, but maybe.
Anirban.
And I think they have a new building now also, if I remember.
Yeah, they have a good, very big building, and he himself told that their auditorium is very, very good.
Well, then
but he is reluctant to take the responsibility still now.
Anirban join করছে 2 মিনিটের মধ্যেই। প্রবলেম করছে।
তাহলে তো ঠিকই আছে।
No, I think they have to hire some few young people there, then I think there will be more energy and perhaps, organization will be possible.
Maybe, yeah.
Because actually now, there are many people, thanks to HRI, now we have so many people looking for jobs, right?
Yeah.
So this is a time to rope a lot of people in.
Otherwise, কি করবে 11টা তো
আমরা পঙ্কজকে তাহলে ইন্ট্রোডিউস করে দিই।
ठीक है, I mean ऐसा कुछ इंट्रोडक्शन के लिए है नहीं, you can just we all know each other, for such a long time, right?
Yeah. Good morning, everyone. Professor Pankaj Agarwal, a renowned scientist at Institute of Physics, Bhubaneswar. He is doing research. He is mainly in high energy physics. Then he shifted to this quantum information foundation, and for a long time he is doing research in this field. Now he is also a very good friend of us, and he has organized many good conferences, schools, workshops in IOP. We all enjoyed there very much. So I invite Professor Agarwal to give his lecture today. Okay.
Sure. So I'm going to share my screen.
Yes.
Just one minute. I mean, can everybody see it?
Yes,
it's visible.
Yes, visible.
Okay. So hello, everyone. Hello. Okay, so today I am going to speak about a work which was done with Chandan Datta and Shobna Bagchi, and this is about inferred uncertainty relations and quantum entanglement. Okay. So obviously, there'll be various parts: introduction, what is inferred and variance, and then what are these relations, some applications, and then conclusion. Okay. Well, all of us know this, right? So that when it comes to quantum mechanics, one of the things which is most popular is not only among physicists, but also among general public is this uncertainty relation, right? So, so this is a part of popular culture even, right? Because this tells you some inherent limitations on knowledge, which one can obtain in various domain of human experience. So actually, and this particular stamp, which was brought out by this German postal agency in 2001 on the occasion of 100th birthday of Heisenberg, typifies it. And as you can see, and which you may want to notice that on this stamp, it says delta P dot delta Q of the order of H. Okay, so thing is, they have written it quite accurately, as it was almost written by Heisenberg in his paper. Okay, so so actually, as we all know, and these relations have come long way since introduction by Heisenberg in 1927, and there was a paper, the physical content of quantum kinematics and mechanics. Okay, so this is in this paper he introduced these relations, and which have now gone in various directions. Okay, just what happened? Yeah. Okay, so these uncertainty relations, they have become actually quintessential marker of quantum features, and they are often used to separate classical from quantum. And these relations actually capture inherent uncertainty in determinism, randomness, which is associated with a quantum system. Heisenberg did not use any specific quantification of uncertainty or obtained any specific bound. He also illustrated this idea using a particular set of observables in a certain experimental setup. So as you already saw on that stamp, right? He was more interested in understanding the physical content than more exact mathematical formulation of this indeterminacy. Okay, so now, so there are all these features which one can generalize. So one can have you want a more precise physical content and mathematical formulation, and so there are many approaches, many different expressions, and many different bounds. So this is actually a vast area. I am just going to touch on a very, very small part of this area. So as we have seen, so there has been the inherent flexibility, which has led to many versions, which are useful in many different contexts. So one flexibility is how to characterize this uncertainty. So depending on how you want to characterize it, you will get different types of relations. And also apart from that, then you could have different lower bounds. So even if you are using same measure of uncertainty, but you can have different bound lower bound. Also, of course, there are some and product type relations where uncertainty of two different observables are either added or multiplied. And we all know they play a very fundamental role, right, in quantum mechanics. Actually, these relations, okay, they've also found many applications. Okay, just to point out just a very, very few, right? Okay, so you can use them as we will see. I mean, people have already done it. To use the relation for entanglement detection, to have a secure key, and see if quantum steering is there or not. So there are many others, okay, applications in wide varieties of areas in physics. Okay, so I have written down some of those applications which we will touch upon, later in this, talk. Okay, so as as you know, that stamp showed you, this Heisenberg wrote down a relation for a set of canonically conjugate observables, say P and Q, and he wrote down the relation like this: P1, Q1, they are of the order of H. Okay, and here, for example, P1 is the precision with which the value of P, this observable P, is determinable. Okay, so he's leaving out, how you want to characterize this precision. So I mean, so there have been all these three types of ambiguities here, which one can use. So first was, so this is a history a bit which everybody knows, but I'm just going over, quickly. So then it was Kennard, okay, who made this relation more precise by using a very specific quantifier. Okay, so he used this standard deviation to characterize the uncertainty. And then he also found a very specific lower bound, which was this h bar by 2. And same thing was obtained by Hermann Weyl also. So, so in this case, we have a lower bound as well as a specific quantifier for the uncertainty. Okay, but the next step was by Robertson, okay, who generalized it beyond canonically conjugate observables. Okay, so he showed that if you have these two non-commuting observables, say A and B, and if this sigma A is the standard deviation in this measurement of this observable, then this sigma A into sigma B is greater or equal to half into this absolute value of the expectation value of this commutator A and B. And this is the relation which we all see in all our textbooks. Okay, so although it is called Heisenberg uncertainty relation, but nowadays I think people would prefer to call it Heisenberg-Robertson uncertainty relation. So okay, so lineage is there from Heisenberg, but this specific form which we see in textbooks is due to Robertson. And he used actually angular momentum operator to explicitly prove it. So as you see, so we have already covered like two features which were left in some sense indeterminate by Heisenberg. So apart from now lower bound, we have a quantifier also, but this lower bound can be tightened. Okay, so it was shown by Schrödinger, just a few years afterwards, that you can add an anti-commutator also on the right-hand side. So in that way, this relation, this bound becomes a bit tighter. Okay, and so here actually I have written down delta square A and delta square B, which are say variance. Okay, square of standard deviation. Okay, so okay, or sometimes you can write as sigma A sigma B, then you take the square root of right hand side. So these are well-known results. Okay, okay, which you will find everywhere. Then of course we have McCone and as well as our own Arun Pati, who obtained some variance uncertainty relations, because what they observed was that if you are in the eigenstate of A or B, then this bound goes to 0. Okay, and so they derived two different uncertainty relations, which were some variance uncertainty relations. So again, you have these observables A and B, and if you sum them, then you will get two terms. Okay, and as you see in the second term, there is a A plus minus IB. Okay. Okay, so this relation is valid for any arbitrary psi, any arbitrary state, and the state orthogonal to it. Okay, so here one can choose sign appropriately. And what you notice that the lower bound is non-zero, for a choice of this psi perpendicular, if psi is not a common eigenstate of A and B. So this is one of the uncertainty relations which they derived. There was another form of this some variance of some uncertainty relation in their paper. Then, of course, Arun also worked with Shrubna to tighten these bounds. Okay, so before going on to inferred uncertainty relation, I just want to give just one example where one can use a quantifier other than a standard deviation to characterize the uncertainty in the measurement of any observable. So especially if you in information theoretic context, one wishes to use Shannon entropy rather than a standard deviation to characterize this uncertainty. Then many groups contributed, and in the end, we had this particular form for this uncertainty relation using entropy. Now, this is a very big area of entropic uncertainty relations. You will find huge collection of such relations as well as their applications, their motivations in many review articles. Okay, so in this specific case, you have this HR plus HS greater or equal to log 2 of 1 over C, where HR and HS, they are actually the Shannon entropies, okay, of the probability distribution of the outcome of measurement of R and S, respectively. And C is a particular number, which was obtained, and then was that this value was proved, okay, by especially this Messina and Ufnik. That is, this is, you maximize over this inner product of psi A and phi J, where they are the eigenvectors of these observables. Okay, so this is entropic, one of the simplest entropic uncertainty relation. And then it was, of course, generalized. Okay, if you have another system with which your system is entangled. Okay. Okay, so these are just some examples of well-known uncertainty relations, which tells you that you can use many different quantifiers, or you can obtain different bounds, and you can use, okay, now of course you can use any two commuting observables, so, and in two non-commuting observables. So in that way, all are general, but you can still use different quantifiers and obtain different lower bound, and which people try to tighten them. Okay, apart from that, of course, there is this whole area of because if we know, as we know, that Heisenberg illustrated his uncertainty relation using a specific measurement process. So there is a whole line of research, okay, on this error disturbance uncertainty relations, so which is gone in a slightly different direction. But we are more interested in these preparation-based uncertainty relations. Okay. So in this inferred variance case, we have two parties. Okay, Alice and Bob, who have with one qubit each. Okay, so and these qubits can be entangled. So two parties sharing an entangled pair of qubits. Okay, so these qubits are especially separated. Okay, so we will call them, say, A and B. Now we can measure two non-commuting observables on these subsystems. Okay, and which one you can call R and S or P and Q, whatever. Now, when these subsystems are entangled, then one can predict the result of measurement on A based on the result or measurement outcome on B. So what our main task is here, to what extent we can predict the result of measurement on A based on the outcome of the measurement on B for two non-commuting observables. Okay. So we shall use this uncertainty quantifier again as variance, but so we'll be using quote unquote a variant of this variance called inferred variance. Then one can obtain uncertainty relations using this inferred variance which are called inferred variance uncertainty relations. Okay, so what we mean by this inferred variance, we will see in a while. Okay, so in literature, there is already, uncertainty relation involving this inferred variance. Okay, so suppose you have some two observable S and Q, which are non-commuting, and if they are measured, and then if you use this inferred variance, then this is a relation where L is some lower bound, for this set of observable, which depends on the state that one uses. Now this relation has been shown to be a signature of the Epr steering criteria. Now we know all states which are steerable are also entangled. So violation of this relation will show that that there is entanglement. So actually, at this read, so this actually here, this, you may say this whole area was started by this Reed, actually, Professor Reed, and they also showed, you can use this relation as an entanglement detection criteria. Okay, so what we are going to do, we are going to go beyond it and show that this lower bound can have a measure of entanglement. Okay, so we shall obtain sum and product uncertainty relation for a 2-qubit system based on this inferred variance. Okay, so what is this inferred variance? Okay, so again, as we have already seen, we have a situation where we have two observers, Alice and Bob, who have 1 qubit each. So inferred variance of an observable S as measured by Alice would depend on the measurement outcomes of Bob. So actually, we are just here, writing down this definition, which was introduced by Reed, and also how to compute these inferred variance. Okay, so suppose, so there is Alice, then there is Bob, and, they are measuring these, especially what we call these poly observables. And so there are two of them, say labeled by say 0, 1, and also Bob's side 0, 1. Then if you want to get outcome I and J, okay, and then as we know, this is so if this system is corrected by density operator rho AB, then this is our probability of this outcome I and J. So once we have this joint probability distribution, we can get marginal one. So for example, we can sum over the outcome of Alice, and then we have this probability of getting outcome J on the Bob side. Okay, so now using this joint probability distribution and this marginal one, we can obtain this conditional distribution. So this conditional probability distribution, as we know, this is conditioned on the measurement, by the measurement outcome of Bob, right? J. Remember, I correspond to Alice and J for Bob. Okay, so then once we know this joint probability distribution, we can obtain this conditional probability distribution. And once we have this conditional probability distribution, we can define this mean value, which you can call conditional mean value. So this conditional mean value on Alice's side is based on this conditional probability distribution. Okay, so Xi, these are the measure outcome, these are the measurement outcome on Alice's side. Okay, and J is a particular measurement outcome on the Bob side. So, as you can see, this is a conditional mean value because it depends on the measurement outcome of Bob. Okay. So now using this particular mean value, okay, one can find what is known as inferred variance. Okay, so as you can see this definition. So you have a system characterized by this, density operator rho AB. and you are measuring the, or say Alice is measuring this observable S, okay, as well as Bob is measuring. And then, then you take this, xi minus mu j, and then is multiply by this joint probability and just sum over. So this is what is known as inferred variance. So as you can see, this depend on the, measurement outcomes on both sides, but this is what is inferred by LS, okay, because this xi is the measurement outcome of LS. So in that sense, this depends, inferred, when we say inferred variance, it depends whether we are talking about Alice or we are talking of Bob. Okay. So now, so we have one of the tools, which we can use, so which is how to characterize this uncertainty, and we use this inferred variance. Okay, now so one of the things we want to do is sometimes go beyond this existing relation by introducing some measure of entanglement in the lower bound. That's basically the goal. Okay, so for that purpose, one can so if you do the calculation, you will find that you have these connected correlators, okay, which would appear in your calculation. So once you want to calculate this joint distribution, you will find this connected correlator, if you will. So if you have a this bipartite system, A and B are being measured, two observables, and this is a correlation in some sense. You can say measure of correlation between A and B. Okay. Okay, so so thing is, this correlator by itself will not take you very far, because it has been shown that if you have a bipartite pure entangled state, so if it agrees, so if it has a non-zero value, then that would mean there is entanglement in the state. And also in the case of mixed state, it is actually not very clear if it has a non-zero value, state would be entangled. Okay. So what we want to do, find what are the connections between this correlator and some other well-known measurement, okay, monotones, if you will. Okay, some function which characterize the entanglement and which satisfies various criteria which a measurement quantifier should satisfy. Okay, so the second tool, and here actually there is a very interesting result by this Pope and Sirac and their collaborators. Okay, so so they have shown that the entanglement as measured by concurrence of a 2-qubit pure state is given by these connected correlators if you maximize them over all set of arbitrary Pauli observables. By Pauli observables here I mean what is written at the bottom, that is you have a measuring this Pauli operator in some specific direction. Okay. Okay, so so what they have shown that if you maximize it over all directions, then this is actually equal to the concurrence of that state. Okay, so here we have this connected correlator, and on the other hand we have this concurrence which it is related to. So one can use it while trying to introduce some measure of entanglement in the uncertainty relation. So, and second, okay, so but that is about pure state. Okay, but more generally our state will be a mixed state. Okay, so in that specific scenario, actually, which has been explored by many authors, so it has been shown that there exists something called G function, okay, which is defined in this way, which is sum over this arbitrary, some, if you have this correlator for arbitrary Pauli observables, it's sum over, so there are 3 independent one, and then it has been shown that if it is more than 1, then state is entangled. Okay, so it is a kind of entanglement witness. Okay, that it has to be more than one. It can be less than one and state may still be entangled. Okay, may not be. Okay. So we have these two tools. Okay, so now we can obtain these relations. So here is the main result. Okay, so for any two arbitrary Pauli observables, so you have S and Q, and an arbitrary 2-qubit density matrix, then this is a relation. So you have this inferred variance for S and Q, which if you sum them, then there is this sum of this local uncertainty. Okay, so this A means uncertainty on the LHS side, okay, or on system A. Minus this, you have this correlators, okay, say for SS and QQ. So which is, so they, denotes this these correlators. Okay, so as you see, this is an equality, but here you have this connected correlators. Now, when I will use when I want to go to this actual measure of entanglement, then this equality will turn into an inequality. Okay, so I'm not going to do the full proof of it because it is not very illuminating. Only thing is you want to use a very general density matrix. You calculate various observables because we know they are Pauli observables. Okay, then you also calculate these connected correlators, and then one can find that this inferred. So if you find this expression for inferred variance in terms of N and M, okay, and R and S, they are quite complicated. So this is where quite a bit of work was required to rewrite that expression in terms of these quantities, which has this local uncertainty as well as this connected correlators. Okay, so if observable S is measured, so then this is the inferred invariance for S and analogously for Q. Then of course you can add them and you will get that particular expression. Okay, but here real thing is how to get then these uncertainty relations. Okay, so what we see that this really involves inferred variance, local variance, as well as connected correlators. Okay, now what we will do, we can use a relation of these connected correlators with concurrence and G functions. Okay, so we will first see what are the expression for some inferred variance and then for the product of the inferred variance. Okay. So main point, as I was telling, would be that the lower bounds would depend on the entanglement in the state. So one can use these relations to detect, measure, and have other uses of this entanglement. Okay, so first thing is you suppose I have a pure state. Okay, so some arbitrary pure state psi AB. Okay, so as you see here again I have sum. And then I have on the left hand side of inferred variance, right hand side I have this this local uncertainty given by this local variance, but now it has turned, our earlier expression has turned into a inequality with the introduction of this concurrence C. Okay, instead of having this connected correlators, and and one can easily obtain this relation from our earlier expression by using the fact that this largest value of these correlators, for that you have to maximize over all of them. So it means that this CC max will be always greater or equal to this CC, say any QQ. And then we know this CC max is related with concurrence. So you can just put concurrence there. So main point here you notice is that for a pure state, this uncertainty relation has concurrence in the lower bound. Similarly, one can obtain a relation for the mixed state. Okay, and in this case, instead of if you see here, so you have a sum over this local uncertainty, then this expression in a square bracket is multiplied by concurrence. You will get identical relation for a mixed state, except this C will be replaced by G. Again, if we use this this definition of G concurrence, we will get it. Okay, so here we are relating then these sum of these inferred variance with some measures of entanglement or some entanglement witness in the case of mixed state. One can do, okay, there we sum, you can also then multiply. And again, you will find these multiplied expressions will also will be related with concurrence in the case of pure state, and with the G function in the case of mixed state. Okay. Okay, so these are the relations which we have. Then of course you can look at some examples. Okay, so in particular, suppose you go to pure state, then you can so actually this is very interesting relation, okay, which can be used for applications. Okay, so for that we use some specific observable sigma x and sigma y. If we use those specific observables in this case of this general pure state, then we get this exact relation. Okay, so if you have a sum of this invariance uncertainty for sigma x and sigma y, then this is equal to 2 minus 2c square, where c is concurrence. Okay, so as you can see here, if you can measure inference variance, inferred variance, then you can calculate or you can measure the concurrence of the state. Okay, and this relation, as we will see, can also help in Qkd. Okay, so this is for pure state. Okay, and for some uncertainty relation, but one can also look for what happens in the case of product uncertainty relation. So if I use sigma x and sigma y there also, then actually this I don't get an equality. But what we see here, okay, so here I have what we have plotted is red one. Okay, is the left hand side, the expression of blue and red correspond to right hand side and left hand side of our this here. Okay, so we have this product in where uncertainty relation. There's this left hand side and there's this right hand side. So in this case, we don't have exact equality, but as you can see, we have a bound, okay, which is for any state. Okay, we have this bound. Okay, so now I think in the few minutes that are left, so I will talk about interesting applications. Also, this inferred variance uncertainty relation have their own fundamental importance. Even if you don't want to talk about applications. But but if you could measure inferred variance, then you can use these relations for many practical purposes. Okay, so if you want to measure inferred variance, as we have seen, all you have to do is measure the joint probability distributions, which are done for example in Bell violation case. So what we will do, we will see three applications. One
Pankaj, means there will not be that much time probably.
No, yeah, I'm just taking 3-4 slides, right?
Okay, fine.
Okay, I have about 5 minutes, right?
3-4 minutes, okay.
Yeah. I will not take more than that. Okay, so because I have just 1 or 2 slides each for each case. Okay, so in the case of inferred variance uncertainty, you can use them as witness also. So for that, as we just discussed a while ago, this left hand side would depend on whether we are talking about inferred variance for Alice or Bob. Okay, then if I turn around those relations, I can rewrite like this. Okay, then but CA and CB, they will depend on whether I'm using inferred variance for Alice or Bob. Okay, so using these relations, actually, if I can rewrite the C square, which is that function. Okay, whether it is more than this max of CA and CB. If you have a non-zero value for C, that will tell you that there is entanglement. Similarly, if you have G is more than 1, you will see there is an entanglement. Okay, so this can act as an entanglement witness. Okay, so as we saw that if you have a very specific observable sigma x and sigma y, you have an exact relation. So what you see here, you can even measure entanglement in a pure state by measuring these inferred variances. Okay, as you see from right here. Okay, So now let me go to this last application, which is this Qkd protocol. Okay, again, just one slide, I think. So actually this protocol, if you remember this Epr protocol, where we use these entangled states, right? And then you can detect the presence of Eve by looking at the violation of Bell inequality. Now, if you are using a maximally entangled state as a resource, okay, then if your C is equal to 1, okay, and this expression when C is 1, right hand side is 0, right? Okay, so like in the Epr protocol, Alice and Bob both can measure these observable sigma x and sigma y. And using these measurement statistics, they can compute the left hand side. If it is other than 0, then there is a presence of E. So an interesting thing is, as compared to Epr protocol, you need to measure only sigma x and sigma y, okay, which can help you to establish the key, as well as if you use a full measurement statistics, even to detect the presence of Eve, which is unlike the case of Epr, where you have to use extra measurements. So actually in the case of Epr protocol, your key rate will be only 1/9, because you have to use 3 observables by Alice and 3 by Bob. While in this case, only 2 are to be measured by Alice and Bob. So you have a 1/4 as key rate, okay, which is much better. Okay, so, as my time is up, okay, I am just finishing in time. Okay, so these are my conclusions. Okay, so what we have is inferred variance uncertainty relations for a 2-qubit system. These relations can be of sum as well as product based. These lower bounds of these relations depend on entanglement. In the case of pure entangled state, this lower bound depend on concurrence, which we can even measure, by measuring inferred variance. And also we can use them in Qkd protocol, where I think it may do better than this looking for violation of Bell inequality. So I think Anirban, I have finished exactly in 40 minutes. Okay.
Yeah, so it's open for questions and comments now. And before others ask, I have a query.
Sure.
In the beginning, when you told this, so in Heisenberg's uncertainty principle, is it that in his own paper he never used this greater than equal to sign?
Yes. So actually, yeah, this is very interesting. You see, so whatever is on the stamp is in his paper, he has written exactly what I wrote here.
Yeah, of the order of, not greater than.
Not even h bar h. P1, Q1 is of the order of h, where P1 is the precision with which the value of this P, which is for observable capital P, is determinable. Right, and as you see, this interesting thing is the stamp also shows exactly like that, of the order of h. Right. Okay.
So is that afterwards of Heisenberg, where later he moved to the present signatures like h bar by 2, or he was always using this?
Yes, no, it was not him, right? It was subsequently, this Kennard, he obtained. And then he found this, it is h bar by 2. So it was in the same year. It was 27. Then after a few months.
So this is the historical sequence also.
Yeah. So after a few months, this Kennard found that, okay, if you use, because Heisenberg didn't use any specific, measure for variance, right? Measure for uncertainty. So you have to use some specific measure, right, to be able to get a specific bound. So then he used this, as this standard deviation as a measure for uncertainty.
This is very interesting.
Anirban,
any other questions?
Anirban, I am Guru Prasad. I have a question to ask.
Hello, Guru.
Anirban, can you go to your last slide where you show the application in cryptography?
Yeah.
So you come to this last point, Qkd Protocol, where you use just 2 observable on both sides. Actually,
in the case of Epr, if you want to have security, you have to use 3 observables on each side. Because only then you can see Bell violation, as well as you can establish the key.
No, but I just tell you that in 1992, Bennett, Bashad, and Marmin also gave a protocol where they use just 2 observable on both sides, and they gave inequality, violation of which would imply we'll say that whether EV is there. So Epr protocol was modified by Bennett, Bashad, and Marmin in 1992, published in PRL. Maybe you can compare your results with Bennett, Bashad, Marmin. That will be better.
Yeah, no.
That is popularly known as BBM protocol.
Yeah.
Okay. Yeah, okay. I will look at that. Okay, thank you.
Any other question? So if not, let us thank the speaker once again and move for the next talk. Our next speaker is Debarshi Das from Satyendranath Bose National Center for Basic Sciences.
Yeah.
Share your slide, Debarshi.
Yeah, I'm sharing. Am I audible?
Yes, you are audible.
And my screen is visible now.
Yes, you can just make it full screen and continue.
Okay.
All right, please go ahead.
Yeah.
And you can hide the lower button also. That.
Oh, right.
Perfect.
Yeah. First of all, I want to thank the organizers for giving me the opportunity to present my work here. The topic of my today's talk is robust certification of arbitrary outcome quantum measurements without using entanglement. And this talk will be based on this archive submission. And this work has been done in collaboration with Anando Debashish and Professor Archam Majumdar from SN Bose Center. So it is well known that realizing any quantum information processing task or communication task or computational task require some particular quantum devices, where quantum devices implies either quantum states or quantum measurements and quantum processes, etc. And whenever any quantum device is received from an unknown or untrusted providers, it is very much important to critically check the proper functioning of the devices. And this is not only true for quantum devices, it is also true for classical devices as well. Without guaranteeing the proper functioning of any device, successful implementation of any task is not possible. So there are various protocols in order to characterize unknown quantum devices. For example, quantum tomography, fully device independent self-testing, certification, and there are many more protocols. Quantum tomography is the traditional method to characterize an unknown quantum device, but there are some limitations. For example, some prior knowledge about the dimension is required here. And also, in order to perform quantum tomography of an unknown quantum device, some other fully characterized quantum devices are required. For example, in order to perform tomography of an unknown qubit state, one must perform measurements of these 3 Pauli observables. So here, these fully characterized Pauli observables are required in order to perform tomography of an unknown qubit state. On the other hand, fully device-independent self-testing uniquely identifies quantum devices based on the measurement statistics alone. Here, there is no need, there is prior knowledge about the dimension or other fully characterized quantum devices are not needed here. But in general, Bell non-locality and hence entanglement is necessary for this purpose. And the most popular fully device-independent self-testing is presented here. Consider the well-known Bell scenario. In this scenario, if one obtains the maximum quantum violation of this Bell CHSH inequality, then we can say that the shared state is maximally entangled 2-qubit state, and the observables are some particular Pauli observables up to some local isometry. So in between these 2 protocols, self-testing and tomography, there lies a lot of protocols, and certification of quantum devices is one of such protocol. It uniquely identifies quantum devices based on the measurement statistics and some partial information about other quantum devices. So this certification requires less amount of information or characterization compared to tomography, but more amount of information or characterization compared to fully device independent self-testing. So the focus of my today's talk will be on certifying quantum measurements having arbitrary number of outcomes. A lot of papers have already proposed certification methods of quantum measurements, but most of these proposed protocols require either entanglement or some assumptions on the measurements to be certified. For example, recently in this paper in NPJ Quantum Information, quantum measurements with arbitrary number of outcomes have been self-tested. And this self-testing is based on the Satwa-Bell inequality, which was proposed in this PRL paper. And obviously, this self-testing requires entanglement. So, what we ask, can we certify quantum measurements with arbitrary number of outcomes without using any entanglement? Because entanglement is a costly resource, and it is difficult to protect it against environmental interactions. So any protocol that does not require entanglement is always preferred. And we answer it yes, but under certain assumption. So the scenario that we consider consists of a preparation device P and a measurement device M that perform one of the four possible measurements A1, A2, A3, or A4. And each of these measurement has small d number of outcomes. So in our scenario, the state prepared by the preparation is subjected to the measurement device, and then the post-measurement state is again subjected to this measurement device. And the measurement statistics thus produced can be described either by the joint probability distributions, which is usual process. Alternatively, one can use the Fourier transformation of the joint probability distribution. In this case, the generalized expectation values is defined in this way. And here AI, K, AJ, L are the Fourier transform generalized observables. Now, if the measurement of AI is projective, in that case, the operators AI, K are unitary. And this can be interpreted as the kth power of AI. That means this condition holds in case of projective measurement. Now, we make this assumption. The preparation device P prepares the maximally mixed state of dimension capital D, where the dimension capital D is unknown. So, in order to perform our certification, we don't need to know the dimension of the preparation, but we trust that the preparation device always produce maximally mixed state. In order to avoid any confusion, capital D is the dimension of the preparation and small d is the number of outcome associated with each measurement. So this notation will be followed throughout this talk. At first, we have presented a lemma which states that if the measurement statistics of any measurement AI satisfy certain condition, then the measurement of AI must be projective. Next, we propose the temporal inequality, which consists of some temporal correlation functions. And this is the classical bound of this inequality. And this inequality is derived from the assumption of macrorealism, originally proposed by Leggett and Kirk. So this inequality derived by us can be considered as a generalized version of Leggett's inequality. The original Leggett's inequality consists of binary outcome measurement. On the other hand, this inequality consists of quantum measurement having arbitrary number of outcomes. And this involves correlation function in Fourier transform space. Here I want to mention that the structure of this inequality has been inspired from Sato-Bell inequality that I mentioned just few slides earlier. But this inequality is conceptually different from Sato-Bell inequality, because Sato-Bell inequality involves spatial correlation, measurement statistics performed by two spatially separated particles. On the other hand, our temporal inequality involves temporal correlation, measurement statistics on a single particle. Next, let us consider that each measurement AI satisfies this condition for all outcome. So, following our just previously mentioned lemma, we can say that each measurement AI is projective. Under this condition, the generalized expectation value can be written in this form, and then the left-hand side of the temporal inequality can be expressed in this form, where this beta the operator beta has this form. Now we define some operators, and using these operators, we can write down this sum of square decomposition of our temporal inequality, valid only for the maximally mixed initial state. And since this is the sum of some positive operators, we can write this relation that quantum violation of our temporal inequality for the maximally mixed state is always less than or equal to 4D minus 1. So this is the maximum quantum violation with maximally mixed initial state. Now let us focus on the binary outcomes case. In this case, the temporal inequality reduces to this form, and in binary outcome case means small d is equal to 2. And in this case, for any input state, not only for maximally mixed state, but for any input state, this condition is valid. But this condition is true only for binary outcome scenario. And using this relation, it can be shown that the earlier mentioned sum of square decomposition is valid for any input state, not only for maximally mixed state. Earlier I mentioned that for arbitrary outcome scenario, the sum of square decomposition is valid only for maximally mixed state, but for binary outcome scenario, this decomposition is valid for any input state. So the maximum quantum violation of our temporal inequality is 4 with any input state for in case of binary outcome scenario. Now using these results, we have shown that there exist at least 2 sets of preparation and binary outcome projective measurements that achieve the maximal violation of our temporal inequality, but the measurements in these 2 sets are not unitarily connected, which implies that without any assumption on the preparation, one cannot uniquely certify the measurements from the maximal quantum violation of the temporal inequality. That is why some assumption on the preparation is necessary, and we have considered one particular assumption, that the preparation always prepares maximally mixed state. Now let us consider this d-dimensional generalization of sigma z Pauli matrix denoted by ZD, and also consider this another d-dimensional observable TD, and here ZD and TD are unitary operators with eigenvalues omega to the power I. That means ith power of unity. Now, let us present the main result of our work. Suppose that each measurement AI satisfies this condition for all outcome. That means each measurement is projective. And also the magnitude of quantum violation of the temporal inequality is 4D minus 1. That means maximum quantum violation is achieved. Now, if these two condition is satisfied, then the four observables A1, A2, A3, and A4 are unique up to some low unitary freedom. That means using this condition on the probability distribution and using the maximum quantum violation of our temporal inequality, we can certify these four measurement settings. I will not describe the proof, but I will just say the mathematical tricks used in our proof is inspired from the self-testing proof based on the Sato-Bell inequality, which was proposed in this paper. But obviously, this self-testing proof is different from our certification proof conceptually, because one involves Bell scenario, entanglement, and our proof does not involve any entanglement. It involves temporal correlation. Now,
Devarsha, move a bit faster to finish on time.
Okay. Just looking at this temporal, just looking at this observables, it can one may not be familiar with such measurement settings. But this measurement settings has already been experimentally demonstrated in optical setup, and these measurements are actually the CGLMP measurements, and hence it has wide range of application. For example, communication, reducing communication complexity, quantum communication game, remote state preparation, secure key distribution, randomness generation. So the measurements that we have certified have information theoretic application as well as foundational importance. Next, we have shown that our certification protocol are indeed robust, but I am not telling this robustness analysis. Just I am telling in practical scenario, this condition may not be satisfied exactly, or one may not get the exact maximum violation of our temporal inequality. So in such case, we have shown that if the correlation produced by the non-ideal measurement denoted by this tilde notation is close to the ideal correlations produced by these ideal measurements, then the non-ideal measurements are also close to the ideal measurements. And this is the robustness for the first condition. This is the robustness associated with violation of our temporal inequality. And finally, we have shown that we can certify randomness based on our certification protocol. So if this condition is satisfied and one gets maximum quantum violation of our temporal inequality, then the measurement statistics can certify randomness, and the amount of randomness increases with increase in small d. And finally, just one slide. If an additional, so far we have discussed everything under one assumption, that is maximally mixed state assumption. Now, if one considers another assumption, which which states that for all measurements the Krauss operators are Hermitian. That means any state updates due to a measurement following the Ludar's rule. Then under these two assumptions, only the quantum violation of our temporal inequality is sufficient to certify the measurements. So if we take this additional assumption, then one need not consider this condition for certification. So finally, in summary, we have proposed certification protocol of quantum measurement without using any entanglement or prior knowledge about the dimension. And our certification requires preparing capital D number of mutually orthogonal pure states in different experimental runs randomly, so that on average, the initial state becomes maximally mixed state. On the other hand, tomography of such measurements requires around the square number of characterized preparation. Now, we have proposed temporal inequality based on the structure of Sato-Bell inequality, and this provides a general methodology for introducing new Leggettgard type temporal inequalities following the structure of different Bell inequalities. And also, our certification protocol provides a general methodology for proposing certification schemes of quantum devices without requiring entanglement based on the existing certification protocol in the Bell scenarios involving entanglement. So, thank you. Hello.
Thank you, Devarshi, and it's time for questions, comments, short questions.
Can I ask a question, Anirban?
Please continue.
Yeah, Devarshi, can you go to your inequality?
Hello.
Devarshi,
Yeah.
can you hear me?
Yeah.
Yeah, can you go to your inequality? This two. Yeah. So how you will calculate these joint probabilities? Means we start with a completely mixed state. We first perform one measurement, and then what will be the update? State update.
State update. State update. We have taken. First, we have considered if this condition is satisfied, then the measurement is projective.
No,
Okay.
but that is our aim to verify. No, that is our aim to certify.
Yeah, and in order to prove, we have taken an arbitrary Krauss operator. That means arbitrary unitary times square root of the POVM operators. We have not taken any particular state update rule.
No, but your second measurement is on the updated state, no? That's what I'm trying to understand.
Right. So what you are asking, which type of state update rule we have used, right?
Yes.
And we have not used any particular state update rule. We have used a general state update rule, which involves the Krauss operator, some unitary times square root of the POVM element. So it is a general state update rule. We have not used any particular state update rule.
Okay. Maybe I'll have to a little bit in details. I have to look into that. Okay, no problem. Yeah.
But if you consider one particular state update rule that I have taken here, this assumption, if I take the Luder's transformation rule, then our certification does not can only be proved using our inequality. If you take Luder's rule, if this is taken as assumption, then this condition is not required for our certification.
Okay. Thank you. Yeah, thank you, Anirban.
Any other comment? Devarshi, means, if I remember correctly, in the beginning you told that it is not yet in archive. Is it so?
Yeah, it is in archive. This is archive.
It's in archive.
But in the archive, it is not updated. This is an old version. The updated version is not in the archive.
Okay. So, thank you, Devarshi, once again for a nice talk and an exciting topic. And now we move to the next speaker. Our next speaker is AVS Kameshwari from Vellore Institute of Technology, Tamil Nadu. And the title of the talk is Role of Entangling Operators in Duopoly games. So it's over to Kameshwari. Please share your history.
Good afternoon, everyone. Sir, is the slide visible?
Yes, visible and perfectly audible. Please continue.
Okay. Good afternoon, everyone. First of all, I would like to thank the organizers for giving this beautiful opportunity to present my topic, that is role of entangling operators in duopoly games. So this work is based on our paper, Cournot and Stackelberg duopoly games in the purview of modified EWL scheme, published in the journal Quantum Information Processing in the year 2021. And this is the author list. So this is the outline of my talk. And now I'll straightly move to introduction to game theory. So firstly, we need to know what is game theory. Game theory is nothing but a mathematical model to study the decision making between the competing agents. The competing agents can be anything, like it can be 2-player, it can be 3-player, it can be anything more than 2. So game theory became more popular in the year 1944 by the work of John von Neumann and Oscar Morgenstern, that is theory of games, by the work that is theory of games and economic behavior. So in this work, they have talked about the classical game setting, and then the quantum version of the classical game was further introduced by D.A. Mayer in the year 1998. So in this I'll mostly talk about quantum game theory. So the components of a game. Now, why do we need this? So these components are needed in order to identify any real life scenario. Like how can we identify a particular thing is a game or a not game? So if the game has all following components, that is a player's set of tools, the strategies which the player adopt, and the payoffs, then we can say that particular thing can be called as a game. Now here, I have given an example of the payoff matrix, also known as the game table, through which we can identify for what strategic combination, what kind of payoff a player can get. I have given an example of two-player, two strategy game. One can also have a game table for three-player as well. Now, this is the overview of entire game theory. It has classical part and a quantum part. So classical part known as a classical game theory, in which the payoff depends upon the initial state of the game and the strategies of the game. This is a classical game theory. Now we go to quantum game theory. In quantum game theory, the payoff not only depends upon the initial state and strategies, but also on the entanglement. So now the question is how to go from classical game theory to the quantum game theory. So this can be done by using certain quantization schemes. So the quantization schemes shown here are EWL, also known as Isert-Wilkin-Livingston quantization scheme. Then we have Mercator-Weber quantization scheme and a newly proposed modified EWL quantization scheme. Now we look, why do we need a newly proposed scheme? Okay, EWL, Mercator-Weber are the already available quantization schemes. Now both the schemes considers classical game as a subset of a quantum game. Now this is one of the drawbacks, because if we want to look into the quantumness of a quantum game, like we say how quantum a quantum game is, so in that cases, using these schemes, we cannot completely answer that question. And also both the schemes, they have only one class of entangling operators, that is the controlled unitaries, of which C0 is the well-known 2-qubit entangling operator. Now, seeing the drawback of both the schemes, we have proposed a new scheme, that is modified EWL scheme. Okay. In EWL scheme, it is known that classical game is a subset of quantum game. Now, and this is because of the following commutated conditions, that is the entangling operator J commutates with the tensor product of the strategies. This is the case in EWL scheme. In modified EWL scheme, we see that the entangling operator does not commutate with this particular strategic combination. So we modify this thing, okay, and then we got a new entangling operator J, wherein C1, C2, C3, which we can see in the matrix, are nothing but the geometrical points of the three-dimensional wave chamber. And this actually gives a geometrical representation of the 2-qubit operators. Now, since we have been talking about duopoly games, I would like to introduce what duopoly games are. Duopoly games are the market games, okay, in economics, which involves two different markets. Since the name is duopoly, we have to, if it is having more than two market games, two different manufacturers, then we call it oligopoly. In our work, we have focused only on duopoly, and that too Carnot duopoly game and Stackelberg duopoly game. Carnot is a simultaneous game wherein two firms, like two market firms, they move at the same time. In Stackelberg duopoly game, firm 1 makes first move, firm 2 sees what firm 1 is choosing, and then based on that, firm 2 decides to move. It is also known as leader-follower game. It's like a common name for the Stackelberg duopoly game. And then there is also another game under the duopoly game itself, that is Burton and duopoly game, which we haven't worked on yet. Now, I would like to discuss more about Carnot duopoly game. So since I've told it's a simultaneous game between two different firms, let's say firm 1, firm 2, and both the firms move at the same time. Okay. Now the quantities which the firms provide in the market, let us call the quantities as Q1 and Q2. And then we have the payoff function, which is given in this equation, where A and C, where A denotes the capacity of the market and C denotes the marginal cost. And the entire theoretical background of this corner duopoly game is can be found in the following references. And this corner duopoly game, the quantum version is studied only so far using Lido-Mesar minimal quantization scheme. But in our work, we tried to study this classical corner duopoly game, the quantum form of this scheme, using modified EWL scheme, and we tried to look from that dimension. Now, this is the mathematical framework of the corner duopoly game in modified EWL scheme. First, we have the initial state. I have taken the initial state as a simple one, as 0, 0. And then the strategies of the firms, like U1 denotes the strategy of firm 1 and U2 denotes the strategy of firm 2. And we have theta here. The theta has a range of 0 to pi. That is, when theta is 0, then U1 and U2 become identity. When theta is pi, then it becomes a flip operation. So we have talked more about identity and flip operation. Also, we have talked about the other combinations as well. Then we have the final state of the game that is given as such. And upon measuring the final state of a game, we get the following quantities. That is, Q1 and Q2 now becomes this, which depends upon the strategies, also on the entangling operator J. Now, in equation 2, we can see the Nash equilibrium point given as x1 star and x2 star, which is same because it's a simultaneous game. And then on substituting these Nash equilibrium point on the main profit function, we get the following equation, that is equation 3, which denotes the final profit function of the firms at the Nash equilibrium point. That is also depends upon the strategies, that is A, B, C are nothing but that contains the strategies which is there in U1 and U2. So, and then C1 is the entangling operator J. Okay. So we take this equation number 3 and then we plot the following graphs, figure 1 and figure 2. So from the plots, from both the plots, actually these two plots are for different initial states. First one is for initial state 0, 0. The other one is for initial state 1, 1. Okay, this is done in order to find what is the role of initial state in the game. So from here we see that when the players adopt same strategies, that can be seen here like this. Theta 1 is 0. Theta 1 is for firm 1. So I have taken the strategy of firm 1 as identity. I have fixed firm 1 strategy. Now, now firm 2 strategy is variable. That is, it is from the range 0 to 5. So we have taken different strategies for firm 2 for a particular firm 1 strategy. Now from the graph, it can be seen that when theta 2 is 0, that means firm 2 also adopts identity operation. In that case, we observe a straight line. Okay, the straight line, this blue line represents for the strategic combination identity, which is adopted by both the firms. We see that it is a straight line. We can say that the profit of the firms, which is given in y-axis, does not depend upon the entangling operator C1, parameterized by C1, when the firms adapt same strategies. Now, for the other, for other strategies, like say for 45, 90, 135, and 180, we see that entangling operator does not, entangling operator actually depends upon the profit. Like one can tune the profit of the firms depending upon the entangling operator. So this is what we have identified here. And also we see as entangling operator J increases, that is from 0 to 45, the profit function also increases, but this again can be tuned with an appropriate choice of the strategies adopted by firm 2. Okay, now we move on to Stackelberg duopoly game. So Stackelberg duopoly game is a sequential game. Therefore, we adopt backward induction, and then we obtain the following Nash equilibrium points as shown in equation 4. And also, when we substitute these Nash equilibrium points to the profit function, we get the following profit function at the equilibrium point, which is given in equation 5. So we have taken equation 5, and then we have plotted the following graphs, figure 3 and figure 4. In figure 3, we can see that when firm 1 adapts identity, okay, then firm 1 strategy is theta 1 is 0, and firm 2 for the arbitrary strategies adapted by firm 2 at maximum entanglement, that is C1 is pi by 4, we see that the red line denotes firm 1's profit function. Purple line denotes firm 2's profit function. We see that firm 1's profit is more than firm 2, and the green line denotes the difference in the profit function of both the firms. In figure 4, we see the difference. Actually, in figure 4, we have plotted the difference in the profit function of both the firms. So here also we see that when the strategies of the firms are same, that is when θ1 is 0 and θ2 is also 0, that is denoted by a blue line, it's again a straight line that is parallel to the x-axis, which amounts to say that the difference in the profit function of the firms also does not depend upon the entangling operator when the firms adapt same strategy. So this is what we have seen graphically for both quantum corner duopoly and quantum Stackelberg duopoly. Based on this, we have following two results. First, in theorem 1, we show the insignificance of entangling operator when the firms adapt same strategies. Well, we have seen when firms adapt same strategy, then it's a straight line parallel to the x-axis. That is, the profit is a straight line parallel to the x-axis. So this is the proof of the theorem. That the theorem states entanglement decides the outcome of the firms only when the firms adapt different strategies. Okay. Now this can be proved conversely by taking the strategies of both the firms as same. Now when we do that, we see the quantities of the firms, that is Q1 and Q2. There is no parameter which has entangling operator here. It is only purely strategies here. So there is no dependence of entangling operator when the firms adapt same strategy. So this is the theorem. So, but we see when firms adapt different strategies, then the dependence of entangling operator comes into picture. Now the other one is significance of entangling operator when the strategies of the firms are interchanged. For this particular statement, this is the theorem. What we have done is, now we have taken the strategy, we have interchanged the strategies of both the firms. Then we got this particular profit function given in equation 7. Now we have the profit function in equation 3, which is the old one, and profit function in equation 7 right now is a new one. We try to equate both of them. Actually, we try to see whether will there be any change if we interchange the strategies of the firms, and if there is so, can we nullify the change? That is our question. So we try to find that on interchanging the strategies and equating the old and the new one, we get equation number 8, and this equation 8 is satisfied when C1 is pi by 4. Okay, so for this particular strategy, for this particular entangling operator J, that is C1 is pi by 4, C2 can be anything in the range 0 to pi by 4, and C3 is 0. For this particular entangling operator, equation 8 satisfies. That is, yes, there is a choice of entangling operator which can equalize the profit function of the firms, of both the firms, in fact, the old and the new profit function of the firms for this particular choice of entangling operator for pure strategies. Similar calculation can also be done for mixed strategies, and on doing so, we got for mixed strategy, the identified entangling operator is a special perfect entangler. Okay. So this is the final conclusion, that we have seen that entangling operators do not play any role when the firms adapt same strategies, and they play a significant role when the strategies of the firms are interchanged. And once again, when there is no entanglement, we both the duopoly games can be we can get back to the original classical form if there is no entanglement. That is also proved. And for mixed strategy, as I have shown in the theorem earlier, the identified entangling operator is double C naught, okay, which is once again a special perfect entangler. And special perfect entanglers are those which can maximally entangle a full product basis, and they have maximal entanglement. Also, we have seen that the difference in profit function of the leader and the follower firms can be tuned with an appropriate choice of entangling operators. Finally, Our entire analysis points emphasizes this particular point that both quantum Carnot duopoly and Stackelberg duopoly does not only depends upon the entangling operator, it also depends upon the initial states and also on the strategies adapted by both the firms. Thank you.
Thank you, and it was a nice talk and finished on time, but now we have enough time to take some questions, comments.
Yes, sir.
Any question? So if not, let's thank the speaker once again for taking us to a different paradigm of quantum game. And it was a wonderful talk and give a good introduction to quantum games also. And now we would move to the next speaker, Chirag Srivastava, who is from Harishchandra Research Institute, Prayagraj. And Chirag will speak about recycled entanglement detection by arbitrary many sequential and independent pairs of observers. So over to Chirag, please share your screen.
Yeah, thank you, sir. So can you see my screen?
Yes, your screen is perfectly visible.
Yeah. So first of all, I would like to thank the organizers for giving me this opportunity. So the topic of my presentation is recycled entanglement detection by arbitrarily many sequential and independent pairs of observers. This work is on arXiv and done in collaboration with Mahashweta Pandit and Professor Ujjwal Sen. So in this talk, I'll talk about a sequential detection of entanglement and also compare it with the previous results present with respect to Bell non-locality. So first of all, we know that entanglement along with the principle of superposition forms the heart of quantum mechanics. It acts as fuel for protocols like quantum teleportation, dense coding, quantum cryptography, etc. Also, quantum mechanics features a Bell non-locality since there exist bipartite quantum states which violate the inequalities satisfied by local hidden variable models. And their application is like device independent key distribution, self-testing, and other device independent tasks. One more point is that we know that all Bell non-local states are entangled, and not all Bell non-local states are entangled. So a brief history about the sequential detection scenario. So first of all, it was first introduced in this PRL paper by Ralph Silva, Nicola Gisa, and the collaborators. So in this, there exist two observers, spatially separated, sharing an entangled state. And their task is to detect entanglement, and at one end of the bipartite system, there can exist multiple observers, and their task is to detect non-locality. So in this paper, they studied the Bell non-locality thing. So their task is to detect the Bell non-locality with the single Alice. So later on in this paper, it was shown in this PRL paper by Brown and Kohlberg, it was shown that an arbitrary number of bobs can share Bell non-locality, CHSH Bell non-locality with a single Alice. So let's go on. So very recently, this protocol is extended to a pair of observers. That is, multiple Alices can also be present along with multiple Bob. And each pair, like Alice 1, Bob 1, Alice 2, Bob 2, has the task to detect the entanglement starting from the state row AB1 shared between A1 and B1 observer. So here it is conjectured in this paper that not more than a single pair can detect CHSH Bell non-locality. So it is quite striking that in the case when there was only single Alice was present, an arbitrary pair, an arbitrary number of Bobs could have witnessed Bell non-locality with single Alice. But when we relax the observers at the Alice's end, that means they can be also multiple in number, then not more than a single pair can detect Bell non-locality. So it is very, since Bell non-locality imply entanglement, but the inverse is not true. So it is also important to ask whether sequential detection of entanglement also has such limitations. Because in the only multiple Bob scenario, entanglement will also be can be detected arbitrary number of times, since non-locality could have detected arbitrary times. So whether this limitation is also present for entanglement in this scenario, in the scenario of pair of observers. So we ask this question, and in fact we show that actually arbitrary pairs can detect entanglement. Whereas for non-locality, there is a conjecture that not more than one pair can detect the non-locality. So, so let's discuss some prerequisites required to study that sequential detection of entanglement. So we know entanglement witnesses are a very important and very nice tool to detect entanglement of an entangled state. So briefly, it is given by an Robertson operator W, whose expectation value can be evaluated with respect to the state whose entanglement has to be detected. If the state is separable, then the expectation value is always greater than equal to positive, and there exists some entangled state for which the expectation value of the witness operator will be negative. For example, consider a Bell maximally entangled state in 2x2 Hilbert space. Then the witness operator corresponding to this state will be given like this in terms of, it is written in terms of local Pauli operators and identity. So the benefit of writing this is that this expectation value of W operator can also be evaluated locally by party A and party B. So this will be used. So therefore, I have written witness operator in this form. So let's go on. So another requirement is unsharp measurements. So for multiple observers detecting entanglement or Bell non-locality, this is another requirement, because if you perform sharp measurement, a lot of information will be gathered due to the measurement, and the state will be destroyed more compared to when you perform unsharp measurements. What I mean by unsharp measurement, I'll tell in the next slide. And so here it is. Suppose consider observable P, and it has and consider a dichotomous unsharp measurement corresponding to the observable P. So dichotomous means two outcome measurement. So here it is, E0 lambda and E1 lambda. So lambda is the sharpness parameter. Lambda has to lie between 0 and 1 for this set to be a measurement. And for we can see that for lambda is equal to 0, it's a trivial measurement, because both the operators reduce to identity operator. And for lambda is equal to 1, it is a sharp measurement, since for example, if you replace P by sigma z, then identity plus sigma z and identity minus sigma z by 2 are nothing but the eigenstate of sigma z observable. And due to these measurements, the post measurement state, we use the Loider's rule as the post measurement state for the protocol. So this is the Loider's rule. So now coming to the main task, that is entanglement detection by arbitrary sequential pairs of observers. So for here in this slide, I will give the general prescription. So let kth Alice and Bob pair, denoted by ABK, share state rho ABK, and the witness operator given like this. Now we have put lambda for the sigma x observable, sigma y observables, and not for sigma z. It means that it is assumed that sigmas Alice and Bob each have 3 settings: sigma z, sigma x, sigma y, but the sigma x and sigma y settings are unsharp, whereas sigma z setting is kept sharp. This is required to show that the arbitrary sequential pairs of observers can detect entanglement. Now, we can so clearly we need expectation value of WK for the state rho ABK to evaluate the witness function. So for that, we can individually calculate sigma z tensor sigma z expectation value, sigma x tensor sigma x expectation value, and sigma y tensor sigma y expectation value. So this can be shown to be equal, can be written in terms of the expectation value of sigma z tensor sigma z with respect to the initial state shared between Alice 1 and Bob 1, rho AB1, like this, where lambda k's are given like this, capital lambda k's are given like this. So sigma x and sigma y are on equal footing, so they will be same. And rho ABK can be written in terms of rho AB1 using this Lloyder's rule, where these are the measurement operators at Alice's and Bob's end, defined like defined earlier here for observable P. So here observables are sigma z, sigma x, and sigma y. So and lambda i's are the sharpness parameters. So from this you get rho ABK in terms of rho AB1, the initial state shared by Alice 1 and Bob 1, and that you can use to calculate the expectation value of this correlation function sigma z tensor sigma z in terms of the correlation function with respect to the initial state. So so consider now, so this was general prescription. Here the state was rho ABK, just a symbol. Here now we take a maximally entangled state first and see that what is the condition so that the state is entangled. So for that, lambda 1, which is the sharpness parameter of the Alice 1 and Bob 1, should be greater than 0. After putting this condition, we get this. And for the kth state, kth Alice Bob pair, the state will be entangled if this condition is whole. So this condition, so these two conditions combined, we can make a sequence for lambda k like this, where epsilon is something greater than 0. See, this is nothing but this right hand side of this inequality. So we can put 1 plus epsilon here, multiply it, and epsilon is just greater than 0. So we can make it an equality. So this is that, and this is defined like, so this sequence is defined like this, that if the previous lambda Alice Bob sharpness parameter is between 0 and 1, then the next Alice Bob sharpness parameter will be given like this. And if this quantity is not between 0 and 1, then the next elements in the sequence are not defined. Here I have denoted it by infinity, and by that we mean that they cannot detect the entanglement. They cannot share and detect the entanglement between them. So as long as all the lambdas are between 0 and 1, those many pairs of Alice and Bob can detect the entanglement, otherwise not. So our task is to prove this. Now this sequence that is defined here, this sequence is can be shown to be increasing and thus positive, since the lambda 1 was needed to be greater than 0 for first Alice Bob pair to be detect entanglement. Therefore, since this sequence is increasing, therefore each term is positive in the sequence. And also one can check that this sequence has also a very good property, that each term tends to 0 simultaneously. That is, if lambda 1 tends to 0, that implies lambda k tends to 0 for all k belonging to a natural number. So therefore an arbitrary number of pair of observers can detect entanglement if the first Alice Bob pair share a maximally entangled state. Now, yeah. So now we go to another class of states So consider all pure states and a class of mixed states. So we can see that psi alpha up to local unitary, any entangled state, not all pure state, all pure entangled states. So any pure entangled state up to local unitary can be written like this. And if we consider a class of mixed states like this, mixture of psi alpha and 0, 1 and 1, 0, then using the same witness operators and measurement strategy, we can get this sequence, which is almost similar to the previous sequence, with new terms like 4p1 and square root alpha into 1 minus alpha in the denominator. And again, this has the same property of as the earlier sequence, and therefore for all k belonging to n, it is possible to have lambda k between 0 to 1. So these class of states also provide that property of arbitrary sequential detection of entanglement. Another interesting class of state that we considered, since we know that so these states, we can see that these states are Bell non-local. That I have not included why they are Bell non-local, but if for example for p1 is equal to 1, psi alpha, this all pure entangled states are Bell non-local in 2 cross 2. So therefore these states are Bell non-local, and we detected entanglement of them arbitrary number of times by arbitrary number of pairs. But here we considered another kind of state which has not CHSH Bell non-local, that, and we term it as Bell local state. So this is the state, and it is one can check that it is not Bell non-local. Necessary sufficient criteria is given in this paper by Horodechkis. So using this state also, theta is the parameter here. We can show that for theta tending to 0, the state has a property that arbitrary sequential pairs of observers can detect entanglement. So this is all. Now I'll conclude. So it is conjectured that not more than a single pair of observers can detect CHSH Bell non-locality. It is shown that in our work that sequential detection, entanglement detection, has no such limitation, and in fact arbitrary number of pairs can detect entanglement. And initial states are characterized, which certainly will possess such potential property. So for example, all pure state and a class of Bell non-local mixed states, a Bell local mixed state as well. And it is not known whether other states can also have some such property. So thank you for listening.
Thank you, and it was a good talk. And now we are open for questions and suggestions. Audience, anyone has any comment, suggestion, questions?
Hi.
Hello.
Hello.
Yeah.
Yeah. Can you go to the slide where the witness operator with lambda is written?
Okay. Yeah.
Yeah. Is this still a witness operator after
Yeah.
lambda?
This we have proved it. I have not presented in this slide that for every separable state it will be positive. The expectation value will be positive. Yeah.
Okay.
Chirag.
Yes.
Am I audible now?
Yes.
Okay. So you have constructed here a witness operator that depends on.
Hello.
Please continue. In between, voice get disrupted.
Yeah. I did not heard you properly.
Have you checked this?
I did not hear the question properly.
Once again, please repeat the question.
This witness operator depends on the parameter k, and I would like to know that for what value of k this constructed witness operator is optimal in the sense of detection of entanglement, number of entangled states.
Yeah. In the sense of Hello. I think, yeah, for lambda is equal to 1, they are optimal. But if lambda k is, it has been shown that for lambda k, if you put lambda k equal to 1, then they are optimal in the sense that they are just touching the separable ball. But we need here not every time lambda k equal to 1, because we don't want to disturb the state much. So they are not optimal. I think they are not optimal witness operators. Did I understand your question properly? Hello.
Okay, there is something with some network issue.
Okay.
It looks like so.
Okay,
you
okay.
have addressed, and
Okay.
we can. Is there any other question? So thank you again, and we would like to now invite the last speaker of this.
Thank you.
Last speaker of this particular session. So our last speaker is Arun Kumar Das from Satyendra Bose National Center for Basic Sciences, and Arun will speak about resource theoretic efficacy of a 2-qubit entangled state in a sequential network. So over to Arun, please share your slides.
Hello.
Probably you were logging from 2 places, means just making echo. Share your slides too. Arun, share your slides. It's visible. Now speak something, means slides are visible. Arun, say something, means we cannot hear you. You can see your slides, but you are not audible till now.
Yeah, can you hear me?
Arun, you are logged in from 2 places. Please mute in one place. So that's creating echo.
Hello.
Now it's fine. Continue.
Okay, so am I audible?
You are audible, but it will be better if you speak loudly or bring the mic closer.
Okay, now?
Perfect. Continue.
Okay. Thank you to the organizers for giving me. Actually, I am getting an echo from. Can you please leave me from? I think there are 2 accounts that have been linked to this Zoom. Echo আসছে.
You just mute yourself in one of the. You log out from one account, means why are you using 2? Arun, it's one account only. Please speak. Please continue. Now there is only one Arun. Unmute yourself and start talking.
Okay. So can you hear me now?
Yes, yes. Please continue.
Okay, good afternoon. First of all, I thank to the organizers for giving me the opportunity to present my work. So this is the title of my talk, Resource Theoretic Efficacy of a 2-qubit entangled state in a sequential network. And we have done this work collaboratively, and Deborshi Das, Shiladitya Mal, Dipankar Home, Orchones Mojumdar, they are our collaborators. And we have uploaded it on archive. So first of all, I would like to motivate you. So as we all know that entanglement is an expensive resource which is used for many quantum information processing tasks like quantum teleportation, quantum dense coding, quantum key distribution. So we also know that entanglement is very much fragile due to environmental interaction. It gets destroyed. So can we recycle entanglement? So this is our first question. So now consider the following scenario where there are many pair of sequential parties. In one wing there are multiple Alices, and on the other wing there are multiple Bobs, and initially a maximally entangled state psi plus is shared between Alice 1 and Bob 1. Now Alice 1 and Bob 1 wants to detect the entanglement. For that they perform. Hello?
You are audible, please continue.
Okay, so Alice 1, after performing her measurement, he sends the particle to Alice 2, and similarly Bob 1, after performing his measurement, send his particle to Bob 2. Now Alice 2 and Bob 2 wants to detect the entanglement between the shared particle between them. So now we will investigate how many pair of the sequential parties can witness the entanglement. Now the previous talk, Chirag Srivastav has shown that it is possible for arbitrarily many pair of sequential parties to detect entanglement, and we will investigate. We will try to investigate if there is some resource theoretic comparison can be made between two scenarios, where the first scenario, the sequential scenario, the entangled state is sequentially shared by multiple parties, and in the non-sequential scenario where there are, instead of maximally entangled state, the pair share many pair of non-maximally entangled state. We will try to draw a comparison which one is more advantageous from a resource theoretic point of view. So to detect entanglement, we need a Hermitian operator W, which is the entanglement witness operator, which satisfies the following condition, that trace of W rho E is negative for a entangled state rho E, and it is non-negative for all separable state rho S. Now the optimal entangled witness operator for a state psi plus, it can be shown, the optimal witness operator takes the following form. Now to recycle the entanglement among multiple pair of sequential parties, they must have to perform unsharp measurement. If they perform sharp measurement, then the entanglement will be destroyed by the measurement. So the subsequent pair of parties cannot detect entanglement. For that, we have to apply the Unsharp measurement formalism, where the effect operator corresponding Alice has this following form. Here Xi is the sharpness parameter for Alice, and for Bob the effect operator has the similar form, while lambda is the sharpness parameter for Bob, and the post measurement state is given by the Luder transformation rule. Now, in the Unsharp measurement formalism, the entanglement witness operator takes the following modified form, where the Unsharp parameter for Alice 1 and Bob 1 comes into the picture. Now, for Alice 1 and Bob 1 to witness the entanglement, this condition has to be satisfied. After the measurement of Alice 1 and Bob 1, the state shared between Alice 2 and Bob 2 is given by this following form. Now here we have assumed the condition that Alice 2 does not know what measurement setting Alice 1 has taken and what outcome he has obtained. Similarly for Bob 2 also. And we have also taken another assumption that the sharpness parameter for all possible measurement settings of Alice are same. Like Alice can take 3 different measurement setting X, Y, Z, but the sharpness parameter is same for all possible measurement setting. Now, similarly for Alice 2 and Bob 2 to witness the entanglement, he has to satisfy this condition. Similarly for Alice 3 and Bob 3. And with our assumptions, it is possible for at most 3 pair of parties can detect entanglement with the following conditions. Now, in the previous talk, we know that arbitrarily many pair of observers can detect entanglement if we leave the assumption that the sharpness parameter can be different for different pair of parties. Now, with our assumption, it is possible for at most 3 pair of parties to detect entanglement. And now we will draw a resource theoretic comparison between the sequential scenario and the non-sequential scenario. So what is the sequential scenario? Here, a maximally entangled state is reused between the sequential parties. But in the non-sequential scenario, all the pair of parties use a non-maximally entangled state. Now, to draw the comparison, we have to define the following measures: the detectability, entanglement conjugate eta, and robustness of measurement. Now, mathematically, detectability is defined by this following expression, which is the sum of the expectation value of the pair of parties. Now, we have rescaled it by multiplying -1 because as these quantities are negative, so we make detectability positive quantity. Now, we will define maximum detectability, which serves as a tool to experimentally detect entanglement. And by maximum detectability, we have to take a strategy so that we have to take a strategy on the measurement settings so that that entanglement detection will be maximum. So the maximum detectability is maximized over all possible sharpness parameter such that the detectability of individual pairs must be negative. That means individual pair must be able to detect entanglement. So we have seen that in our particular scenario, the maximum detectability is 0.2, which occurs for this particular value of the sharpness parameter. That is Alice 1 and Bob 1 sharpness parameter equal to 0.73, Alice 2 Bob 3 sharpness parameter is 0.8, and Alice 3 and Bob 3 sharpness parameter is 1. Next, we will define another measure, that is the robustness of measurement, which is first introduced on the PRL paper by Skripczyk et al. On 2019. and it is defined by the minimal amount of noise that needs to be added to the measurement such that it becomes a trivial measurement. Mathematically, it is expressed by this expression where M is the POVM measurement with the POVM elements MA satisfies this property. Now, this is the operator norm which is calculated by this expression. Now, in our particular measurement setting, we have seen that the robustness of measurement is equal to the sharpness parameter of our measurement. So now, in our two scenario, the sequential and the non-sequential one, we have addressed the comparison in terms of two resources. One is entanglement consumed and another is robustness of measurement. So we have first asked what is the total entanglement consumed in the non-sequential scenario, with the constraint that in the non-sequential scenario we kept the detectability same as that with maximum detectability in the sequential scenario, and the total robustness of measurement in the non-sequential scenario is same as the total robustness in the sequential scenario. And we have, as we have seen, that for maximum detectability in the sequential scenario, the robustness of measurement is this 5.06. In the non-sequential scenario, where we have used three pairs of, where the three pairs of observers share three Warner state of this following form, where pi is the state parameter. Now, if they have used this Warner state, then the total entanglement consumed is given by the total concurrence, which is by this expression, and the non-sequential detectability is given by this expression. So now our task is to minimize the entanglement consumed in the non-sequential scenario with the constraint that the total robustness of measurement, that is the total resource full of measurement that is used in the non-sequential scenario, is same as that of sequential scenario, and the total detectability in the non-sequential scenario is same as the detectability in the sequential scenario, and that each pair of the observer will able to detect the entanglement. Now, from the table we have seen that in the sequential scenario, where 1 EBIT of entanglement is sufficient, but in the non-sequential scenario we need at least 1.11 EBIT of entanglement, which is greater than 1 EBIT entanglement for same detectability and for same resourcefulness of measurements. Thus, it is evident that sequential scenario has the advantage over the non-sequential scenario. Again, the advantage can be recasted from another point of view, that is, what is the total measurement resource, that is total robustness of measurement used in the non-sequential scenario. So now our task is to minimize the total robustness of measurement in the non-sequential scenario, and with the constraint that we use 1 EBIT of entanglement in the non-sequential scenario and the detectability to be same as that of sequential scenario. Now, from table 2, you can see that the robustness of measurement in the sequential scenario, in the non-sequential scenario, is greater than that of sequential scenario. So the sequential scenario has the advantage. So we can see from this table also. So now what we have seen, that entanglement can be recycled, and the sequential scenario where a single 2-qubit maximal entanglement state is recycled shows advantage over the non-sequential scenario. Thank you for your kind attention.
Thank you. And there are no more questions. So there is a question in the chat box. I would request Ajit Iqbal Singh to please speak the question, and then the speaker can answer it. Kindly read, kindly state the question. So,
Okay, I'm reading it. Is there an ideal number of people you might find? How to spread rumors fast by fan? Ponin and Ponin. I think it is not linked with my.
This is in an old journal, Mathematics Magazine, 1997, and authors are Fan, Poonen, and Poonen. You see, my curiosity was, how many people do you want in the sequence? Does that matter? Like Alice 1, Alice 2, Alice 3 you chose, and Bob 1, Bob 2, Bob 3. So is this 3 important, or any number is fine, or what is the best number?
Okay, so actually we have started with an arbitrarily number of observers. So in one wing, there can be arbitrarily large number of Alices, and on the other wing, there can be arbitrarily large number of Bobs. So initially, Alice 1 and Bob 1 are sharing a maximally entangled state. Now, the question is, how many pair of the sequential observer can detect the entanglement? So this is the question.
No, Anirban, can I make a comment? This is Archana.
Sure, please.
Yeah. So Professor Singh, yeah, your question is important, certainly. So you're asking, I mean, typically, is there an ideal number of people? So now this particular scenario, on which you heard the last two talks by two students, one of HRI and another from Kolkata, actually asked this question in a different context, typically of network scenarios, where there are a number of observers who sequentially approach or access a particular entangled state or states. So now, depending on the situation, what you want in with practical considerations, you could choose a fixed number of people. And so then the question is, do these fixed number of people, will they be able to access the entanglement or some non-local correlation in the given state optimally? So that is the question. And in order to answer this question, various people have tried to see, first of all, address the question, actually, what is the maximum number of observers who can actually work out in such a scenario? And secondly, if there are a fixed number of observers, then what are the settings for which they could ideally access this entanglement or correlations so as to perform some interesting information processing tasks with them? So I think this should address the question that you are asking.
Thank you. Thank you.
Thank you very much. Thank you. Yes, thank you.
Yeah.
Is there any other question? Any other question or comment? So if not, we thank the last speaker and also all the speakers of this session for the wonderful talks, and participants for listening them patiently and engaging in discussion. So the session is over for lunch break, but if the organizers have any announcement to make, please make it, otherwise we can move for lunch.
Okay, thank you, sir.
So from host, is there any announcement to be made?
So yeah, I don't see the host there, but anyway, so we come back at 2 p.m. for the next session, which is going to be chaired by Devashish. So Anirban, thank you very much for.
Okay. Thank you. Bye, Archana.
Hello, Alok. Are you there? Yes.
Yes, Devasita.
Yes. So this is post-lunch session. First speaker of this post-lunch session is Dr. Alok Kumar Pan from NIT Patna. He is a good friend of us, all of us. He is doing basically on quantum foundation, and he's a very good researcher, produced many students within this software. So I invite Alok to provide his talk.
Thank you, Devasista, for this kind introduction. Can you see my screen?
Yes. Yes.
Yeah. Let me full screen it. Is it okay?
Yes. Yes.
Okay, so thank you, Devasista, for this introductions, and I would also like to thank the organizers. I mean, they are very known to us, known to me, and for giving me this opportunity to talk here. And I shall be talking about this network non-locality for arbitrary input scenario. And this work is done with my two PhD students, Neha Munshi and Rahul Kumar. And this talk is mainly based on these two papers. There's one physical review paper last year, and also there is an archive post last year. Quickly to the outline of this talk. The plan is that I shall be very brief about this Bell CHSH non-locality. I mean, this is very known to us, and there are many, maybe few students are there and who are also familiar with this. So this is for the setting the stage of this to introduce the non-trivial network scenario. If you consider Bell scenario is a trivial network, then there's a non-trivial network scenario, which is known as the bilocality scenario. And then I shall provide the two generalization. One is that bilocality scenario involves two parties, and then it can be extended to the n parties, and also the generalization in the sense of that is usually people consider two input scenario for every party, but I consider here this arbitrary input scenario. And there is a correspondence between this Bell non-locality and network non-locality, so that the characterizing the non-bilocality that I shall also discuss. So this Bell CHS scenario very known to us. That is, there's a bipartite scenario. There are two parties, Alice and Bob, and they received the input two inputs. Let's say x equal to 1 and 2, and y is also 1 and 2. And the outputs are always dichotomic shear. And there's a shared randomness. That is, there's a source that they introduce the physical systems to Alice and the Bob, and that we commonly in a classical theory commonly denote it as lambda, the hidden variable. The most important quantity that we are interested in this bipartite Bell scenario is the joint probability. The joint probability PABXY, and in a local hidden variable model that can be written in a factorized form. That is outcome of Alice is independent of the Bob's input and the outcome, and the vice versa. So as we all know that this quantum theory does not respect this factorization. In fact, the quantum theory actually is incompatible with this factorization, and that is commonly and routinely checked through the violation of suitable Bell inequalities. And one of the simplest Bell inequality is this CHSH inequality, where this CHSH is functional beta 2, that is upper bounded by 2. And here A1, A2 are the observables that Alice will choose upon receiving the inputs 1 and 2, and similarly for Bob. As we all know that in quantum theory, we have given a very suitable state and observables, we get up to 2√2, that is violating this CHSH inequality. And this 2√2 is called the Streelson bound. So for this optimization, we require this Alice and Bob's choices of observables has to be mutually anti-commuting, and psi has to be a maximally entangled state. Of course, such a choice of observables can easily be obtained for the qubit system, and psi can be considered as a 2-qubit entangled state. But actually, it is without this 2√2 value can be obtained without assuming any dimension of the system. So qubit example is this one. It's almost a textbook example nowadays, because this A1, A2 are mutually anti-commuting. Similarly for B1, B2, and psi is a maximally entangled state. And that is enough to get this 2√2. Of course, then the I discussed this bipartite Bell scenario, which is the simplest one and the straightforward and trivial generalization of it, the multipartite scenario. For example, if you consider a GHZ state originating from a source and there are three parties, then you can play the similar game. And that's a tripartite game, and that can be easily extended to the multipartite scenario. Of course, a multipartite non-locality has been studied last 2 decades. It's extensively studied by many people. But here we can, I shall be considering a non-trivial network scenario. For example, the tripartite scenario can also be like this. That there are three parties you can see, but that's a difference between the common standard multipartite scenario is that here there are two sources. Instead of one sources, we have two sources here. You can see here that there's a two sources, S1 and S2. So S1 is the source that distributes the physical system to Alice 1 and Bob, and the S2 is another source that distributes the physical system to Alice 2 and Bob. And here this scenario, it's the simplest and tripartite scenario in the, it's called the bilocality scenario, where all the parties, there are two edge parties, that is Alice 1 and Alice 2, and Bob is the central party. They all receive the input, two inputs, and the outcomes are again the dichotomic. There's two outputs. So one most important assumption here, of course, there are two assumptions that we already considered in the bipartite scenario. That's the locality and the realism. This assumption is there. Along with, there is an extra assumption, which is that the sources has to be the independent. I mean, there is no prior correlation between S1 and S2. That means in a hidden variable model, if you consider a local hidden variable model, then they actually can be characterized by the distributions rho lambda 1 and rho lambda 2. So it's a joint distribution if you consider the rho lambda 1, lambda 2, and that can be factorized. So this is an additional assumption in this bilocality scenario. The important quantity again here, like the tripartite joint probability, that is BA1, BA2, that can also be written in the factorized form. So you can see that outcome of A1 is independent of, only dependent on X1 and lambda 1, and is independent of the other Bob's or Alice 2's. And similarly for Alice 2, but Bob's outcome is dependent on two lambdas, that is lambda 1 and lambda 2. So once we get this tripartite joint probability, we can calculate any kind of correlation by using the suitable combinations of the probabilities. Well, so there is this actually scenario was introduced by this Bansier, Gisa, and Pironio in 2010 and 12. They are motivated from the entanglement swapping experiment. So they formulated this nonlinear bilocality inequality, and so nonlinear because root is there, and they derived that this upper bounded by 2. And of course, here the notational clumsiness is there because I shall be introducing the arbitrary input scenario. Let me explain the notations here. Delta 2 here means is that the subscript is for the number of inputs. We have 2 inputs here for every edge parties, and superscript 2 is for the number of parties. So there are two edge parties. So Alice 1 and Alice 2. So that's why this is delta 2. And similarly for J1, J2 can be suitably defined. And you can see here, this part is for the Alice 1, and this part is for the Alice 2, and B for the Bob. And similarly, there's a plus here, but here's a minus. So they introduced this inequality, and they also calculated the quantum values. So in quantum theory, what we can do is that we use two sources, and they emit the two entangled state. Of course, we can take entangled states, so to two entangled states, and there has to be the uncorrelated one. So what we get is that optimal quantum value you get to √2, but it looks similar to the Bell violation, but it's actually not the Bell violation. It is actually a violation of the bilocality inequality. So the required observables for choices required for the Alice 1 and Alice 2 both are mutually anti-commuting, but Bob's observable has to be the mutually commuting. And we need a joint entangled state, which is psi equal to this one. But important fact is that up to now, all these bilocality scenarios are calculated by using the 2-qubit entangled state. So you see that this requirement can be fulfilled in 2-qubit entangled state, but when you actually extend the number of inputs, the 2-qubit entangled state may not be enough, and that we shall be discussing. So for this, we need to introduce a technique that is, these are the choices of the observables that are enough to in the 2-qubit system, and that are enough to get this optimal value to √2. So Actually, the optimal valuation can be obtained easily from the 2-qubit systems. But as I mentioned, that if you increase the number of inputs and your 2-qubit system, 2-qubit entangled state sharing between one Alice and Bob may not be enough. So we introduce a scheme for the analytical technique. That is, of course, it's a sum of square approach, but it's a little modified form. And that enables us to calculate the optimal value without introducing any dimension a priori. So for this, we introduce a positive semi-definite operator, that is a gamma. Again, the 2 is for the number of setting and number of inputs. So gamma, if we can write this gamma is in this particular form, that's a delta, which is the bilocality expressions, and then beta in a positive number. In such a case, whenever this gamma is a positive semi-definite, so when this gamma is equal to 0, in such a case, we can get the optimal value, which is beta. For this, I'm not going to the details of the calculations, definitely, because will not have time. So we introduce a positive numbers, two positive operators, that is M, and that's the polynomial function of the Alice's observable, Alice 1's observable, Alice 2's observable, and the Bob's observable. Using this, we can calculate, we can actually write in its particular form, and that from here, this gamma, we can actually get this one. And that's a suitable choices of the M has to be required. And we introduce this parameter omega 1 and omega 2, and these are actually a number, positive numbers, because we are taking the roots. What finally we get is that we have to do some maximization over these omegas. What are the omegas? For example, this omega 1, 1, that means the omega 1 for the first Alice is that A1 plus A2 it's L2 norm. So this L2 norm can be calculated for this particular psi. And finally, we will get this 2√2, and also the conditions for the optimization has to be this mutually anti-commuting observable for each Alice. And Bob observable can be calculated by using this optimization conditions, and that will turn out to be the mutually commuting. Of course, here the 2-qubit system, 2-qubit entangled state sharing between each Alice and Bob will be enough for this, but for the higher number of inputs, that will not be enough. Okay, so now let me go to the generalization of it. First generalization is the in-locality scenario, and then the second generalization is for the arbitrary input. And this is the bilocality scenario can be straightforwardly generalized to the in-locality scenario. And that is actually, there are many such networks out there. One of the networks I'm considering here in this talk, this is star network. This open network, there are many closed networks as well. And there's another very well-known network is the linear chain network. So in this network, you can see that there are n number of sources. That's a star network. There are it's a generalization from bilocality to n locality. So there's a n number of parties, edge parties, and one central party, and n number of sources are there. And this n number of sources, each of them is emanating a physical system to each Alice and Bob. And the important assumption once again here is that all the sources are uncorrelated. Okay, this is the scenario we had. So in this scenario, for this in-locality scenario, this Androli and Tavakuli, they proposed it's actually a straightforward generalization of bilocality scenario. They calculated this, they proposed this inequality, and then again the quantum value comes to 2√2. But next we generalize for the arbitrary input scenario, because you see that each Alice is receiving m number of inputs, and this Bob is receiving 2 to the power m minus 1 number of inputs. Okay, in this scenario, what we did is that, and again, I have to mention that all sources are uncorrelated, and we introduce a function, and that is we define an expression which is delta mn in this arbitrary scenario, because it is completely arbitrary for m and n. So m actually the number of inputs, and n is the number of parties, number of edge parties in the star network scenario. So we define these expressions, and this is, you can see that I equal to 1 to 2 to the power m minus 1, which is the Bob's number of input. So this jmin looks complicated, and this can be written in this particular form. Important thing is that here, this minus 1 to the power y xki, that will fix the plus 1 or minus 1 here. That means y xki is actually either 0 or 1. So this we have fixed by using the encoding scheme of random access code. Of course, we are not playing the random access code game here. We are just using the encoding scheme of it to fix the whether it will be plus or minus 1 and just before these observables. Okay, this is the Alice's Alice of kth Alice observable and xk equal to 1 to m because of there is an input xk equal to 1 to m and k equal to 1 to n is for the number of parties. Using this and of course using some mathematical technique, using the inequality that is sum of product and less than equal to product of sum, we finally reached to a conclusion that we have to actually optimize this alpha mk with this modulus. And this alpha mk can be written in this form, as I mentioned, that this has to be plus or minus 1 that has been decided by the random access code. For this, we actually considered a random variable that is y delta, which is sampled from 0, 1 to the power m. And that means there are 2 to the power m number of m bit string. So we will actually consider half of it. So we actually will not consider the strings where the first bit is 1. We only consider the string where the first bit is 0. So that will be able to now, once we have it, then it is easier to fix that which of the what will be the expression for it. Of course, it will be a very lengthy one. And then what we consider that for every Alice, there are n number of Alice, and each Alice actually using the similar encoding. So the alpha mk's value will actually be same. That is, we consider alpha m. So the further, if you consider this integration, finally we get the bound of this bilocality, n-locality inequality for arbitrary input scenario. Of course, I have not showing the calculations here. Calculation can be found in this paper. And of course, we have used some Hadamard code, and this derivation is completely analytical. Okay, now coming to the scenario when we have this, we can replace in quantum theory by using by an entangled state, because the lambda was considering in the hidden variable model or in local model, where we can replace them by using a quantum state. Again, they are independent to each other. And then what we found is that, of course, I'm not going to show the derivation of this because this will be a little bit involved here, and one may follow my paper to take a look. And this is again optimized by using this sum of square approach. It's a modified form of sum of square approach. So optimal quantum value we get is a 2 to the power m minus 1 into root m. It is always violating this bilocality, the n-locality bound alpha m. So important thing is that for this optimization, we derive that we need that every Alice has to perform the m number of mutually anti-commuting observables. As we know that if Alice and Bob shares a 2-qubit entangled state, in such a case, Alice will have the qubit system. So in the qubit system, you have at most 3 mutually anti-commuting observables. So since if m is greater than 3, in such a case, you cannot do this optimization by using the qubit system. So you need to consider an entangled state which is higher dimension, which is beyond these 2 qubit entangled states. So we found that one need to take every Alice has to share m by 2 floor number of 2 qubit maximally entangled state with Bob. For example, if you take m equal to 4, in such a case, Alice and Bob, each Alice and Bob shares a pair of 2 qubit maximally entangled state, and that will be giving the optimal value of this one, 2 to the power m minus 1 into root m. So then the joint state has to be in this form. This is the form of joint state we have, and see that every Alice A1B means Alice 1 is sharing the Bob with this 2 qubit maximally entangled state to the power m by 2, and similarly for the every Alice. Well, so but the violation for arbitrary m violation actually gets reduced, and for example, if you plot the ratios between the quantum and classical values, one you can say that actually for the larger m it saturates to 1.25. So we still have a violation, but violation getting reduced. Well, we actually further we have considered the other things. For example, the chained n-locality inequalities. Here in the earlier case, we are considering this I equal to 2 to the power m minus 1, but we can consider all the inputs are m. So in such a case, we can formulate a suitable expression for the n-locality inequality. That is, this is the suitable expression, and this is the definition. It's hard to follow, I understand. And then it was easier than the earlier one to derive the n-local bound, which is 2m minus 2. And again, we using this similar sum of square approach, we actually can optimize this chain in locality inequalities. I would like to point out here is that chain Bell inequality is very, very important, and many people have studied it. But I think that there is a optimization was done in a, I mean, clear-cut optimization was done in a 2004 paper by Weissner. And I really didn't find that whether chain Bell inequality can be optimized for any arbitrary dimension. I mean, without recourse, without referring to any dimension of the system. But I have not found it. So what we did is that we optimize the chain Bell inequality for these arbitrary dimensional scenarios. And that was very helpful. And then using the sum of square approach for the network scenario, we also optimize this, optimize the chain Bell inequalities. Well, this is the result we obtained. It's quite similar. And then let me tell you that what's the relation. I mean, there's a correspondence between this bipartite Bell non-locality with the network non-locality. So there's a very interesting paper by Jisa in 2017, and that they showed that this bilocality inequality, the maximum value of bilocality inequality, can be written in terms of the two CHSH maximum values. For example, like that Alice 1 is performing a CHSH experiment with Bob's first particle, and then Alice 2 is performing the CHSH experiment with the Bob's second particle, and then they are actually kind of related. For example, when this row AB and row BC, I mean, BC means here this row A12, A1B, and A2B. In such a case, if the row, the one of the state violates CHSH inequality, then that actually warrants the violation of the bilocality inequality. But this Jisa's proof is based on this Qkd criteria that is valid for 2-qubit entangled states. And of course, further, it was generalized by Devashish and Indani and this Amit paper in 2020. It is what for the n locality scenario. Again, they have also used these 2-qubit entangled states. But here we derived in our work that is without assuming any dimension of the Hilbert space, because that was required for our further work. Well, the similar result can also be obtained here, because if you characterize the in network non-locality, what you can do is that, for example, this every Bob's observable is actually the tensor product of the kth number of observables. So that, for example, that Alice 1 is actually sharing the first one, for example, B11 with this Alice 1. Similarly, Alice 2, Alice 3 can be seen as there's a kind of bipartite Bell scenarios every time. So we propose an inequality that is relevant Bell inequality in that case can be written in this particular form. And it so happens that it is also alpha M. And then what we can do is that we can link with this violation, maximum violation of this network inequality with this the Bell type inequalities maximum violations. And that means is that whenever one of the alleles with the Bob that violates this Bell inequality, then we'll have the violation of this in locality inequality, and that can be extended. That can also be extended to the other form. For example, with the chain Bell inequality cases, if we write the every Alice is performing with the Bob with a chain Bell inequality violation, and that actually warrants the violation of the network non-locality. So similar results we actually obtained for this paper, and that can also be the rigorous results can be found in this paper with Sneha. And there are some relevant points I have to mention here, that all the network non-locality inequalities I considered in the star network scenario, and that can also be generalized for the case of this linear chain scenario. Of course, we have studied it, but we are not presenting here. So all the network non-inequalities we considered here can actually trace back to a suitable Bell type inequality. So this can be considered as an advantage or can be considered as a drawback. So recently, in a paper by Tavakoli, Jisa, and Cyril Mansiart, in 2020 PRL paper, they showed that there are some bilocality inequalities can be formulated, and that cannot be traced back to the known Bell type inequalities. And they use instead of this Bell set measurement, they use the elegant joint measurement for their purpose. In fact, this work is based on the SDP, and it is really involved one. So recently we have also formulated a kind of bilocality inequalities and also n locality inequalities that cannot be traced back to the to the Bell type inequality violation. So this is not, I'm not presenting here, but given the opportunity, I can present elsewhere. And also you can privately contact me so that I can tell you. Well, so to sum, that I discussed the bilocality and n-locality scenarios in quantum network. I provide two generalizations. There is one generalization is that bilocality to n-locality, that is people have already done. But another important generalization we have done is that this is a non-trivial one, that is extending the scenario to the arbitrary input cases. The two arbitrary cases we have considered, one considered that is all the Alice's in the star network performs this arbitrary m number of binary outcome measurements, but the Bob performs 2 to the power m-1 number of measurements. And the second, it is quite corresponding to the chain Bell inequality, that is each of the Alice's will perform the m number of measurement, and Bob will also perform the central party. He will also perform the m number of measurements. And the whole calculations, we have not considered any dimension, and that is optimized by using an interesting sum of square approach here. And also, finally, we discussed that is all the Bell inequalities, all the network Bell inequalities here considered that can be traced back to a bipartite Bell inequalities. So it is, I mean, there's a new bilocality inequalities can be proposed. I mean, one may think about it to propose more such bilocality inequalities that cannot be traced back to the Bell type inequalities. And with this, I'd like to thank you all very much.
Thank you, Alok. This is time for a couple of questions.
Yeah, I finished almost in time.
Can I ask one, Devashika?
Sure, sure, Manik. Please go ahead.
Yeah, Alok, nice talk.
Yeah, thank you.
So
thank
I
you.
want to understand in general, when two input, two output, or n party, so then there are in those cases all linear Bell inequality, their optimum will be always achieved by some n qubit system, and this result actually follows from this Jordan decomposition, this Majanes theorem. So you are extending it for m number of measurement, all are dichotomic. So
Yeah,
the technique you are applying, is it extendable to any arbitrary linear Bell inequality kind of things? Because all are linear Bell inequalities, no?
Yeah, all linear Bell inequality can be transferred, but the technique I have used to optimize the things, and it will be tricky for tricky to extend, because there's a symmetry. If there's some symmetries there, then it is easy.
In the expression.
Yeah, in the expression, there's some symmetries required. If there's no symmetry, it will be difficult to do it.
Okay. Okay. Some particular symmetry.
Some particular symmetry is required. Yes.
Okay.
For example, if you want to do by using this one, my technique, our technique, if you want to do, for example, the tilted Bell inequality, it will not be possible. So,
no, but what I'm trying to say, then since you can prove this optimal value for any arbitrary dimension, so your technique will be much more useful for a network scenario in self-testing.
Yes,
several kind of self-testing.
It is self-testing. It is self-testing. Yeah, it is self-testing.
Okay. Thank you for the nice talk.
Thank you, Manik. Thank you.
Any other question?
Devashika, you may ask one.
Huh?
You may ask one.
Yes. If there is no other question, I will ask one thing. Because this is online. We are also doing research for many times.
Yes.
So what about the other kind of measure? This elegant measurement you have shown, this what kind of network you are considering?
Okay, the straightforward one was the linear chain was considering. Okay. But the last time we talked there in your Calcutta University also. That is that can be that, as you said, that's any open network can be just a decomposition of either linear chain or the star network. Yes. So I'm actually trying to extend this. I mean, there are many star networks with linear chain that I'm trying to consider. Yes.
So you have found any substantial difference between these usual measurement process and elegant measurement process?
Not yet. It's a very initial stage.
Okay.
Actually, we are thinking something not elegant one. We are thinking something else, and including elegant one. Yeah.
Okay. Thank you. Nice.
I'll report you.
Okay. Thank you, Alok.
Thank you.
Nice talk. Okay.
Thank you, Devasida.
Thank you.
Okay, bye.
Now, is Carol there? Carol?
Hello, good
hello.
morning or good afternoon in India. Yes, I'm here.
Hi, okay. So, Professor Karol Dyskuski, he's professor in physics in Jagiellonian University, Krakow, Poland. And he loves mathematics very well, and he's doing very hard mathematical problem in quantum foundation, quantum information, as a whole quantum theory itself. And basically in entanglement theory, he has done many works. He's a co-author of a nice book I read very early in this Geometry of Quantum State with Ingvar Wengsten. This is really a wonderful book. Students can learn many things from his book. So I invite Professor Karol to give his talk today. His title is 36 Entangled Officers of Euler's Quantum Solution of a Classically Impossible Problem. So Karol.
Thank you. Thank you very much for an invitation to India and such a nice introduction, and for mentioning the book we've written together with Ingemar Bengtsson from Stockholm. And now I have a great pleasure to visit India, and I'm visiting India with Indian results. I'm going to tell you about recent paper and results obtained together with your colleagues from Chennai or from Madras Institute of Physics, so Suhail Rater and Arul Lakshminarayan, and also with my Polish colleagues, Adam Burchardt, Wojciech Bruzda, and Grzegorz Reichel-Mieldziądź. If you have never heard about officers of Euler and how to entangle them, I hope I will be able to explain the problem and give you a solution. In fact, it's not a solution to the original problem of Euler, but it is a quantum solution to the quantum version of problem of Euler, which is known not to have a standard classical solution. First, let me pose much more general questions. What is important in theoretical physics? Well, we pose some important questions. For instance, what is the correct theory to describe the world around us? What is the correct theory to describe the world at the micro scale? Is quantum theory we teach and study capable to describe the world? Or do we need perhaps a generalized theory like higher order theories? How such a generalized theory might look like? If yes, if no, well, if we restrict our attention to quantum theory, let us try to extract as much as possible from the standard quantum rules. In fact, I worked some time ago on generalized quantum theories. I wrote a paper on quartic theory, in which instead of density matrices, one can use density tensors with 4 indices. But today, I will concentrate on the standard quantum theory, and I will discuss some problem of extremal quantum states. So I will define a class of quantum states which will present some special properties and discuss how to find such as states, how to identify, and possibly how to use them. So a very short introduction to the subject. Of course, you know quantum rules. We describe physical systems in Hilbert space. If we have n states which can be distinguished, we use n-dimensional Hilbert space, which is complex. For n equal to the simplest non-trivial case, we have qubit, so quantum bit, so any state can be expanded by a superposition of states 0 and 1, which are orthogonal, and then all the states form the famous Bloch sphere. So pure states are at the sphere, mixed inside the Bloch ball, and any point from the sphere corresponds to such a state. For larger dimension, this is not a sphere anymore. It's so-called complex projective space with n-1 dimensions. So altogether there are 2n, because they are complex numbers, 2n minus 2 real numbers. But look, this space is in a sense similar to the sphere that is isotropic. So there are no points distinguished at all. Well, all states are in some sense equal. So you could say, well, it's a ill-defined problem. There are no extremal states because all of those states are the same. Like all the points at the sphere are the same. Well, this is true to some extent. This is true if there is no structure imposed to the system. Then all states are equal, and basically the question is not well defined. However, if we impose some structure to the system, then the situation changes. And then there are some states which, well, we can jokingly say they are more equal than others. For instance, if we discuss two-qubit system, like one qubit here, one there, here I have two blue pens, one is up, one is down, then of course we can distinguish some class of systems. By the way, can you see my pointer, my arrow here? If I move it at the screen, can you see it?
Yes,
Yes, we can.
Yeah.
Good, good. Then, of course, we can define separable states, and they are distinguished, and also maximally entangled Bell states are also distinguished. So in some sense, we can call those Bell states, they are extremal states in some sense. Well, in a very well-defined sense, because they carry the maximal entanglement, which means the correlations between two subsystems are maximal, and then the entropy of partial trace is maximal. And of course, you know well that those extremal Bell states are important for several applications in quantum technologies, and therefore we are interested in describing such class of states. So for two-qubit system and Bell states, basically everything is known, like for many, many years, almost since 60s, since Bell, and then for, let's say, last 30 years, we know of many interesting algorithms and protocols based on those states. To give you some more mathematical introduction, a short reminder. So we define formally for a bipartite system separable states. They are given by the tensor product. Entangled pure states are those which are not of the above form. Here's the formula of the famous Bell state. There are 4 of such orthogonal states in 4-dimensional Hilbert space. They form a basis. And as I already mentioned, one of the possible definitions is that the partial trace is maximally mixed. But then such a state can be written with the so-called Schmidt decomposition. So you can write any bipartite state in the product basis, and all coefficients are given here by a matrix of coefficients. And then performing singular value decomposition of this matrix, one can replace this double form by a single summation, where those numbers lambda, they are just singular values of matrix C. They are called Schmidt elements of the Schmidt vector. This is Schmidt decomposition, and they give you the weights of this superposition. And then for a separable state, the vector lambda is pure because it reads 1 and all other coefficients are 0. And the other extreme case, if all coefficients lambda are equal, then the state is maximally entangled. But then it also means that today's CC dagger is identity. It's a maximally mixed state. So C is unitary up to rescaling, because CC dagger is proportional to identity. And then indeed the entropy of partial trace, which is equal to the Shannon entropy of the Schmidt vector, is maximal. In the case of Bell states, it's just log of 2. It is easy to generalize the scheme for 2 qubits. Now the generalized Bell state looks like this. It's again the same sum, but we have now D components. And of course, all singular values are equal. The partial trace is maximally mixed. And then the entropy is maximal. Entanglement between 2 qubits is maximal. And this property holds also for all locally equivalent states. So to summarize the simple part, a bipartite state is maximally mixed if partial trace is, the state is maximally entangled if partial trace is maximally mixed, or in the case if this matrix of coefficients is proportional to be unitary. For instance, look at such a state: 0, 0, plus 0, 1, minus, plus 1, 0, minus 1, 1. So, okay, at the very first moment, you might not recognize that it is exactly equivalent to the Bell state. It's maximally entangled. Why? Because this matrix, if you write it down, is 1, 1. In the second row, 1 minus 1, you recognize it's a Hadamard matrix, which is, of course, orthogonal. So, to summarize, for any bipartite state, singular values of such a matrix characterize entanglement of the state by entropy of singular values of this matrix. Now, the question changes. If we have not two parties, but let's say 3 or 4 or more, situation is more complicated. First, what we mean by multipartite? Well, in Latin, there's a statement that 3 makes a collegium, so therefore there's a difference between 2 and 3. And indeed, for me, 2 is not multi, multi starts from 3. Well, we can also say concerning geometry, 2-dimensional objects, okay, they are flat, have only area, no volume. 3-dimensional, well, it's a great difference. They have already volume. For our life, of course, 3-dimensional means more than 2. So for me, this is just a simple statement definition, is n equal or more than 3. Now, from a more algebraic perspective, why 3 is such a difference, is different than 2? Well, I told you, you know very well, it is not difficult to work with matrices. We can diagonalize them, find singular values or eigenvalues, find its rank of a matrix. This is not a problem. However, if you take 3-party system and you decompose it in any product basis like I, tensor J, tensor K, then all those expansion coefficients, they form a tensor. So object with 3 legs, 3 indices. And now algebra tells us that working with tensors is much more difficult than working with matrices. And of course, people study tensors for many, many years, but it is not so simple to work with singular value decomposition for tensor. Basically, the direct generalization of the singular value decomposition of matrices does not exist. It's not even easy to compute rank of a tensor or norm of a tensor. So therefore, you see a great difference between algebraic object with 2 indices, like a matrix, which corresponds to bipartite system, and tensors with 3 or 4 or many indices, which corresponds to multipartite systems. Therefore, you see immediately that working with multipartite is really, really much more difficult. So in some sense, I can write a stage equation that 3 is much, much, much larger than 2, concerning the amount of work you have to invest to understand the problems of systems of 3 or more parties. So now a simple open question. If you take a state with n subsystems with d levels each, which state is extremal? Extremal, for instance, in the definition, which is the most entangled. And as you can guess, there is no good answer to this question, in a sense that it depends on the measure of entanglement used. In the simplest multipartite system of 3 qubits, we have HA, A times HB times HC, so 8-dimensional Hilbert space, H2 to the power 3. And there are famous states like GHZ states with 2 terms, or W states, here look, with 3 terms, and they are different. Moreover, not only they are different, they cannot be somehow locally converted one into another, but in a sense, both those states are maximally entangled. It only depends on the measure of entanglement. For instance, GHZ states has such a property that 1-partied reductions are maximally mixed, like in the case of Bell states, which is not the case for W. However, W has another advantage. If you consider, take 3 parties and put away a single let's put this object away. So you trace over one subsystem, GHZ state is not entangled anymore after partial trace, and W remains entangled even though you removed one system tracing over the subsystem. So in a sense, you see that from one perspective, GHZ is the most entangled, from another W, and we see that this question is not exactly well posed. Basically, depending on your needs, your applications, the measure of entanglement you use, different states could be called the most entangled. And now I will make a break, a short pause concerning discussion of entanglement, and I will remind you some very, very basic notions concerning combinatorics, and perhaps we'll discuss later on quantum combinatorics. So I will mention an important paper, in fact, PhD thesis by Zauner, who, from my perspective, founded the idea of quantum combinatorics. But what is a classical combinatorics? Well, you know very well, there are different objects of classical combinatorics. We basically deal with discrete numbers. One possible aim is to describe designs. What are designs? There are special configurations of objects with some symmetry and balance. I will give you a very simple example. Let us take 4 aces, 4 kings, 4 queens, and 4 jacks, and we wish to arrange them into array 4 times 4, such that in every row and every column there is only a single card of each suit and only single card of each rank. This is a definition. We impose some conditions to have some symmetry and balance, and you see here a very nice example. We have exactly such a constellation of 16 cards which satisfies those conditions. Very nice. I'm sure you have seen it many times. However, mathematically speaking, this object is called Greco-Latin square. Why Greco-Latin? Because Euler used Greek letters for ranks and, let's say, Latin letters for suits. So each card has 2 features. Here is ace of spades, or in the letters of Euler, it was like A alpha. Or they are also called 2 mutually orthogonal Latin squares. So one Latin square is, let's say, composed of suits, second of ranks, and the statement they are orthogonal means that all those cards are different. So there are no 2 cards with 2 symbols equal. So there's a question. For what dimension such nice combinatorial, classical combinatorial designs do exist? Of course, they do exist for d equal 4, because I have given you an example. And as you can guess, they exist for d equal 3 or d equal 5. However, strangely enough, there's no such a configuration for d equal 2. This is simple to see. If you have 2 aces and 2 kings, the problem has no solution, because if you put, let's say, here, start with ace of, let's say, spades, and put here king of hearts, in the second row, you cannot do anything, because all kings will be in the first column, or in the second column will be repeated, or there will be colors of the same color in the same line. And it's not difficult to construct such objects for d equal 3 and 5, because they are prime numbers. For 4, it's also possible. It's a bit more tricky. It's possible because 4 is 2 times 2. So it's a power of prime. Sometimes one uses the notion of mutually orthogonal Latin squares. So there you can take not only 2 squares, but 3 or more. And mutually orthogonal means that all of them are orthogonal mutually. So all those symbols are different. In general, you can show that there exists not more than d minus 1, those mutually orthogonal Latin squares. And of course, for d equal 2, this d equal minus 1 is 1. So there's not such a great surprise that there exists only 1 orthogonal Latin square of size 2. However, a strange thing occurs for d equals 6. Namely, this bound gives you d minus 1. 6 minus 1 is 5. So in principle, one could say, we know there are no more than 5 mutually orthogonal Latin squares of size 6. However, Euler discussed this problem himself more than 200 years ago, and he found that there are no more than a single Latin square of this size. And he posed a problem which is now called famous problem of 36 officers. Why officers? You know, he was then working in St. Petersburg, and there are rumors that even the Tsar, it was a she, Catherine, she was fond of organizing parades of her officers, and somebody showed such a configuration of 25 officers from 5 different ranks and 5 different regiments, and they ordered such 5 times 5 squares. So there was a question whether one can do it better. And if you have 36 officers of 6 different ranks and 6 different units, each unit had a different uniform. So to make it nice, they wanted to order them in such a square in front of a Tsar. So you see, there was a kind of a applied grant, military applications, yes, very simple. And Euler was really very much engaged into this problem. And he really, you know, was Euler, and he worked hard on it. And even he was not able to give a proof that such a configuration does not exist. He only was sure it is so. And he stated that no solution exists. So we confirmed there is no classical solution of this Euler problem. It was proved only 121 years later by a French, by the way, not a mathematician. He was a kind of a lawyer. He worked outside France in Algeria. So again, rumors say he has nothing better to do in Algeria. Only basically he was checking one by one all possibilities. It was not so like this. His main achievement was that he managed somehow to see that among those millions of possibilities, there are really millions of them, he can divide them into the classes, and he found some of order of 1,000 or 2,000 classes of possible solutions. And then he could check that among all those possible class of solutions, there is no real solution to the problem. And he published his paper in 1900. So it was a first formal proof that Euler was right concerning this statement. There's no solution of the Euler problem of 36 officers. So it means there exists no a pair of orthogonal Latin squares of size 6. Well, now let me ask, are there any questions at this point? Is this clear? Are you with me? Can you hear me?
Yes.
Good. No, it's good for me to know. I regret I'm not in India with you, so at least that you are not at the afternoon nap and some of you are still there. So thanks, yes, for answering my questions from time to time. It is just easier for me to know that somebody is there and is listening to me. Well, here I will just show you it's kind of a game. But now look, here you see such an object 6 times 6. And you have indeed 6 different colors. It corresponds to different uniforms, different regiments, and different ranks. So ranks consider, you see here, different heights. So in a sense, like general, colonel, lieutenant, and so on, for each color, you have officers, so those figures of different height. So here, by the way, this was called 36 cube. This was the game for kids. And now you can buy it in a shop. It's like 10 or 12 years old. It was sometimes called the world's most challenging puzzle. But look here. It looks like the solution of Euler problem is found. In each row, each column, you can see there are objects of different height and different color. So how do you think? Was Euler wrong? I was really amazed. So my nephew had such a game. I played with it a long time. And of course, Euler was right. So mathematically speaking, such a solution does not exist. And as you can guess, well, it depends how you call it. It can be a cheating or let's say physical imprecision. So let's say mathematically, of course, he was right. But here, to be honest, there's a catch. So there are 2 objects here which look like they are of height 5, but in fact they are of height 4. So there are 2 objects here which in a sense do not satisfy all those conditions. Color conditions are satisfied, but height conditions are not satisfied. So this is the answer, but still the game is very nice, and this gives you a flavor how to work with the Euler problem. So if you manage to see such a game, I'm really very much convinced it's very good to give it to your, let's say, kids or nephews to play a bit, but also to enjoy mathematics and also physics behind it. So now we go back to quantum case. So we discuss now only homogeneous systems, so systems with all subsystems of the same kind, and we define now a class of states. They consist of n subsystems of d levels each, and we call such a state absolutely maximally entangled. Look, so AME, n subsystems d levels each. If for any choice of n half subsystems trace out, the reduced state is maximally mixed, which means if you take 4 objects like here and you split into any symmetric pairs, like 2 here to there, and you perform partial trace, this state is maximally mixed. So which means that for any composition of the subsystem, one part is maximally entangled with second part. So this is the idea behind. There are important papers to quote of Scott, Facki, Helvig, and Arnaud, and many others. And of course, Bell state, well, it's also sometimes called one uniform state, so just such an AME state. However, a very important statement. Strangely enough, there are no such AME states of 4 qubits. This was resolved by Higuchi and Sudbury, and I will argue that this statement, which was known now for 20 years, means that if you have maximal entanglement between A and AB, 2 qubits, and CD, they will not be maximally entangled for another partition or yet another. You cannot have maximal entanglement in all 3 partitions. And this is related to the fact that we will not find generalization of the orthogonal Latin square of size 2, even in quantum case. Then there exists such objects for 4 qubits or 6 q-quarks. They are easy to find. Well, not only they are easy to find, but they are easy to relate now with those objects I discussed before. So Greco-Latin squares. So here is exactly Greco-Latin square of Euler. Now you see the name Greco-Latin square. In each column and row, there's a single letter Greek and Latin. If you like to play cards, bridge, this is the same constellation in the bridge notation. Here's information notation. So of course, 0, 0, 1, 2, and so on. Those numbers denote letters or cards. And now the claim is that such a nice object is applicable to explicitly write down such an absolutely maximally entangled state of 4 qubits. So I claim such a nice state is directly encoded in such a pattern, which gives you a relation between orthogonal Latin squares or states. How to get it? Look, very simple. Let's take this last information design. So we have 3 times 3 squared. So each box can be labeled by 2 numbers. Let's say here is 0, 1, here 0, 2, and so on. And now in each box, there are 2 digits. So what we do, we put 2 black digits of address, and we put inside 2 red digits we read out of this pattern of those cards. So to be precise, here I put 0, 0. Now the address is 0, 1, and I find here 1, 2. So I put those numbers here. Now in the address 0, 2, I find numbers 2, 1, or queen of diamonds. So I put 2, 1. In the next row, I do the same. So here is 1, 0, and the contents is 1, 1, and so on. So now you see, you have 9 terms, which correspond exactly to 3 times 3, 9 squares, boxes from this square, and you get such a state. And then it's not difficult to see that this is indeed a maximally entangled state, in the sense that if you split it into 2 parts and perform partial trace, then the partial trace is maximally mixed. And this is just guaranteed by the fact that you have no repeating cards or repeating ranks in each column or row. Moreover, this object, this state, is equivalent to the quantum code because you can encode single Qt in this case into a free Qt state. So here's the coding. How you do it? Well, you put together all states from the first row, which start from 0, and you say 0 is given by 0 tilde, which is obtained by superposing 3 states starting at 0. So those, let's take the blue part. You see this last row corresponds to this state. You will recognize that those digits are the same. And this code has a special property that if you have one flip of any Qt, you can still decode the original information because the distances between those states is free. So you can easily find information if you assume that there was only one flip. Well, so this works for size 3, also 4, also 5. Now a question why we care about such a problem. We care because the such states are important for many different applications like quantum codes, teleportation. For instance, if you have a 2-qubit Bell state, you can teleport 1 qubit from A to B. If you have generalized Bell state of size D, you can teleport 1 qubit from A to B. If you have a 3-qubit GHZ state, you can teleport 1 qubit between any users. If you have 4 qubit GHZ, you can also teleport 1 qubit between any 2 or 4 users. But if you have an AMA state is maximally entangled. So irrespectively which pair of users you will choose, you can teleport 2 qubits between one pair to other pair because both pairs are maximally entangled. So you see there's a direct advantage of those AMA states in contrast to generalized GHZ states. And there are also relations to perfect tensors and holographic codes, and therefore they are studied for the last decade in different fields of physics. So now you can ask for what dimensions n and sizes d those AMA states do exist. Here I quote a table online by Felix Huber and Nicola Widerka. You can find it online. So here you have a local dimension d. Here you have number of parties n. So green means it exists. Red does not exist. So for instance, this red part means that there are no such AMA states of 4 qubits. And white means we do not know. So in 2021, there was here this white spot. So nobody knew whether such states of 4 Q hex, so subsystems of size 6, do exist. This question was open. And to answer this question, well, we were not aware whether such states exist or not, but we learned about the interesting idea like quantum Latin squares. Latin squares is a nice notion, and basically every good notion can be quantized. There was a very nice paper of quantum Latin squares by Musto and Vicari. It was later generalized in our paper with Dardo, Goshenece, and others. But the first paper on quantum Latin squares is this British of Musto and Vicari, and the idea is very simple. So you know what is Latin square? Quantum Latin square is instead of numbers or colors or cards, like here 0, 1, 2, 3, you are allowed to put here any superposition, like Bell state. And now a standard orthogonal Latin square is the set of objects which are different in different column and row. So quantum analog is almost the same. We only assume that in each column, each row, all states are orthogonal. So look, you have to have orthogonal bases in each row and column. So here you see, of course, in the first 2 columns, in the first 2 rows, of course, they are classical rows, so they are orthogonal because they are different. Here, we rotated in some subspace a bit. Here, they are like Bell states or other states from this paper, and you can easily see that not only both lower rows form orthogonal bases, but also in all columns you get orthogonal bases. So this is a very simple example of a non-trivial orthogonal Latin square. In short, standard combinatorics deals with discrete symbols like 1, 2, 3, 4, 5 up to D, and a group of permutation because we can change the order. And now, in some sense, quantum combinatorics, we replace the discrete set of symbols by a continuous family of states. Of course, the continuous family because they are superpositions, so each state can be in a continuous fashion changed from up to down. So here you have just those continuous superposition. And instead of permutation group, which is discrete, you work with unitary group, which is of course continuous. So this is the main change and main generalization. And then our task was to find a good definition of generalization of orthogonal Latin square. So now quantum version of orthogonal Latin square is a table, but not table of objects, but now a table of states. In fact, table of bipartite states in HD times HD, and they have to satisfy the following properties. All of them are orthogonal, which corresponds to the fact that all cards are different. And now we had a constraint that in each row and each column, all colors or all ranks of a card or officers are different. And this is replaced by the following equation that if you expand such a state by matrices of coefficients, then those matrices of coefficients follow the satisfy the following rule that the summation over first or the second symbol in each row and column gives you identity, which will imply that partial trace of such a huge state, so here is the huge state, here, a four-party, will be absolutely maximally entangled. If you generate such an object which contains d squares bipartite states, which satisfies those three conditions, which are analogous to standard conditions of Euler, to construct standard classical Latin orthogonal Latin square, then the following four-party state, look here, ij tensor phi ij, sorry, so this phi ij is this, so here should be phi ij, is absolutely maximally entangled. So it means that this tensor is perfect, which means that if you reshape it into a unitary matrix, for arbitrary pairing of indices, this matrix is unitary. If you choose mu is like ij or ik or il, all those matrices, three matrices obtained from this tensor are unitary. If you take any tensor, it will not be like this. So it's a very special property of this tensor that for any choice of two indices forming such a matrix out of this tensor, you get a unitary matrix. And this unitarity, like threefold unitarity for any choice of indices, is necessary and equivalent to obtained orthogonal quantum Latin square. So now we pose a question whether this standard Euler problem of finding a pair of orthogonal Latin squares of say 6, which we know that classically has no solution, whether it will have solution if you allow for quantization. So if you allow for looking in the space of states, which means you allow any state, in a sense, it can be entangled. So we are joking, we allow those officers to be entangled. So in other language, instead of working with permutation matrices, in this case of size 36, we ask whether there exists a unitary matrix of size 36 with the required properties. So I think, okay, let me ask a question. How much time do I have? I think 10 more minutes.
Almost 10 minutes.
Yes,
8 minutes.
yes, yes.
8
Okay,
minutes.
so I will have to speed up. So I will not discuss too much that this state also maximizes so-called entangling power. If you have two subsystems, it entangles two subsystems as much as possible. It can be used in those models for bulk boundary correspondence. But, okay, here's one picture of Krakow. Maybe you will visit someday. So Arul at least was there. And here comes the solution or attempt to describe you the solution. So in the case of 4 cube trees, we know how the solution looks like. We take such an object, so standard classical orthogonal Latin square written in the cards or in the number notation. We construct such a state, taking 2 trees from address and 2 others from contents of the square, and we produce such a state. And we know, this is easy to prove, that if we start with the appropriate orthogonal Latin square, this state here written, defined by this pattern, is really absolutely maximally entangled. Why? Because 3 permutation matrices are permutation, they are unitary. So those permutation matrices describe, so let's say one axis will be the address, second will be rows, will be height, rank of the card and color. But then you can choose, for instance, columns and color. So it will be second matrix, or columns and rank, and this will be third matrix. And all those relations have to be bijection, they have to be invertible, they have to be permutation or unitary. So it means that those matrices, one is unitary, and after those operations, R stands for reshuffling, and gamma for partial transpose. You see, they are partial transpose. They have to be also unitary. And this is easy to show. It works for n equal 3. Now, if we go to n equal 6, situation is more complicated. Here is an example which looks like a solution of the Euler problem in one notation of numbers, here notation of cards. But if you look closely, you see that this is not quite a solution. Why? Because numbers 33 are here repeated. So like you see there are 2 queens of diamonds. So by the way, this is just this solution of this game I showed you for the kids. So basically they are this kind of cheating because there are 2 pairs of symbols which are doubled in a sense. So this is a solution which is as close as classically possible. And if you consider this quantity entangling power, it gives you a very high number. The maximal possible in this normalization is 1. And here you get something like 313 out of 315. So only, let's say, less than 1 promile, no, 3 promiles are missing. And now, so here is such a graph which shows you this entangling power. Here's some other auxiliary variable. And basically, we wish to get a matrix, a unitary matrix, which maximizes this quantity. And for such a object, classical object, you get some numbers somewhere here, but they are still far away, or relatively far away from the aim. And now we were for 5 years not certain whether we will find a good solution. And here I have to again emphasize the role of Suhail and Indian colleagues. And we worked and looked for the good way to find this solution numerically, and we failed. And Suhail found basically a good idea and good seed. So here is like a trajectory. He found a good seed close to one of those classical matrices, but not exactly it. And then found a nice, it's called synchron algorithm. Basically, you first check whether U is unitary, then you take UR, which is not unitary but close, you make it unitary by a polar decomposition, and then you perform partial transpose, which is not unitary, and you do it iterating this procedure, and eventually you want to find such a matrix which is unitary, after reshuffling is unitary, after partial transpose is unitary. And here was kind of trajectory, and basically very often this algorithm does not work, but Suhail was very, very lucky, and he found several seeds, so starting points, from which a trajectory really nicely converges to this point. And he found a numerically matrix which does the job. It was a huge matrix, 36 times 36. It was not easy to understand it. And then the point is that you have a freedom of rotating it locally by U6 times U6. And now there was a clever idea how to rotate in such a way to make this huge full matrix sparse. And then my other colleagues, especially Adam and Wojciech and Grzegorz, they first found such steps to make it more sparse than to rotate it by U2 times U3 and found such a matrix. And then they found that if you perform special permutation, those matrices, all of them are unitary, can be taken to such a block form. Now look, you have 9 blocks of size 4 each. And now you can impose unitarity. And now they could guess, or in a sense, knowing those numerical numbers, they could guess an analytical solution by imposing unitarity in each block. So here colors denote amplitudes of the elements. And the solution is in fact given here. So here are amplitudes. So amazingly, it occurs only 3 numbers are important, and here they are analytically given. So C is 1 over square root of 2. So the reddish color means a Bell state with some phases. And A and B are very special because their ratio is the famous golden ratio. Therefore, there are only 3 amplitudes which enter. This is just the square is basically based on Pythagoras theorem. So A squared plus B squared, C squared is 1/2. So they are like Bell states. And 2 other numbers, green and blue, in this diagram, A and B are related to the golden ratio. And only other analytical part is those omega. So omega is exactly a root of 20 of, so you see here a circle, 1/20 part of the full circle to pi over 20, because if you raise them to different powers, so now you see omega to 18 or to 3, you find relation related to golden ratio, to standard Greek geometry, which imply that certain states are orthogonal. Basically, the fact that those ratios are given by this golden number implies that, let's say here in each block, each columns and each rows are orthogonal. Not only that, those red states are just directly Bell states. They have the same amplitudes, but those green and blue, they are locally equivalent to Bell states. So in fact, each such a square, 4 times 4, forms a Bell basis. And Bell basis, of course, you know, all states are orthogonal. So to show you here is a solution in some sense. So here you see we have really 36 officers here represented by cards. And you see that they are like Bell states. Here you see this is just a combination of, let's say, ace of clubs and king of spades. And they have the same size, so same amplitude. Or there are 4 of them which are locally equivalent to the Bell state. But now you say, hey, something is wrong. You have 2 aces here and 2 kings, and you are supposed to say, well, it should be 1 king. Or you say, there are 2 red colors in each column, it should be 1. So first of all, you see that there's not a artifact here. You have exactly 2 red objects in each column and row, to blue to black, which means that there is kind of coarse-grained, nice combinatorial classical structure, where we have 4 copies of each symbol copied 4 times. And then here is the final solution. It is exactly the same solution, but now in the chess allegory. You have 36 fields. Now, each state is represented by 2 or 4 figures. Size of the figure corresponds to amplitude. And the numbers here corresponds to phases. For instance, this at this field A1, you have, look, a black horse. Now 10 means omega to power 10, so it's minus green bishop. And now what you can show that, for instance, the phases imply that, for instance, such a square will form a Bell basis. So then, in a sense, even though there are 2 black objects here or 2 green, they are orthogonal because Bell states are orthogonal. Or even though you can say, there are reddish objects here in such a column or row, they are still orthogonal. So in a sense, this is a good solution to the problem. So to summarize, strongly entangled extremal multi-party quantum states are useful for many, many different aims and different purposes in the theory of quantum information processing. For instance, they are equivalent, they imply some errors of quantum error correction. They can be used in multi-user communication, other protocols. So main result of this work is that absolutely maximally entangled states of 4 parties with 6 levels each do exist. So we found a solution to the quantum version to the problem of Euler. It was first announced in our preprint, written exactly 1 year ago, almost 1 year ago. So 120 years after paper of Tari, which was written 120 years after the original work of Euler. Now this paper is in press and physical review letters. And this result implies that there is this solution of quantum analog of the problem of Euler. There is an optimal bipartite unitary gate which maximizes entangling power. There is a perfect tensor with 4 indices, and it can be used for tensor networks and bulk boundary correspondence. And there is a new, it's called non-additive quantum error correction code. This is the notation which allows us to encode a single Q hex in 3 Q hexes, which does not belong to the class of stabilizer codes, which can be used, for instance, to encode the state of 4 dices. Therefore, there was a picture with 4 dices before. In short, extremal quantum states can be useful. Let me finish thanking once again my Indian colleagues, Indian co-authors, and finish now here with this picture. You see here a state of 4 dices. They are classical dices, but if they were in this quantum state, they would have a special property. If you measure any 2 of those, let's say 2 left dices, you will be able to infer the state of 2 other dices. Thank you very much.
Thank you, Carol. Nice. We are out of time. So 1 or 2 short questions. Ritobroto, you can ask. Ritobroto, unmute yourself.
Oh, sorry. It was a very nice talk, of course. Can you just show me your slide number 26, Carol?
23?
26. 26. 26.
This one?
26. No, that's I think the one next. Yeah. So you have written some kind of a block form of that unitary matrix. I mean, why you get this kind of a block form? I mean, you did not get it always,
look,
right?
Short. We found this numerical solution, but the numerical solution is up to local rotations. So we use those privilege of local rotations times U6 times U6 to find a better representation, so better basis in which this complicated matrix admits simpler and simpler form. So first, my colleagues found this form. Then after second rotation, because U6 can be decomposed into U2 times U2 times U2, they found this form or each block. And now look at this form. So this form, this is the main matrix U. And now if you make additional permutation, you see that this matrix can be written in such has a block, so potentially a block structure. And this was done just to see that in such a block, you can now analytically find unitarity, positive unitarity. You can solve unitarity and get analytical numbers. This was the main issue, to find analytical form of the solution. So in a sense, it was like miracle that it worked, but because I had a clever young collaborators from India and from Poland, it did work.
Any other question? Shivashish, you have?
So am I audible?
Yes.
This is Shivashish Carroll from IMSC, Institute of Mathematical Sciences. It was nice talk. Can you hear me?
Yes. Please go ahead.
Okay, so this is maybe not completely related to what you said, what you talked about this aiming. Now, there were some efforts to define maximally entangled states for multipartite system, in the sense that I'll call a pure multipartite state to be maximally entangled if I divide the parties into two groups, whatever be the group number of elements in each group, then the entropy of the reduced state of at least one subgroup will be the maximum available entropy of that dimension. So for example, this condition is satisfied in the case of say the GHG states. Okay.
Sorry, of what states?
GHG states, the these 3-qubit GHG states.
Yes, yes.
So where the idea is, if I group the 3 qubits into two subgroups, where each one group contains 1 qubit and the other group contains 2 qubits, then the one group containing 1 qubit will have the reduced density matrix, which is having maximum entropy, right?
Yes, correct. But look, but this is nothing in contradiction, because we worked on the system with, let's say, 4 parties, and then we just imposed the very same condition, asking that for any splitting of the system with 4 objects into 2, so you have 2 and 2 pairs, for any splitting, this condition has to hold. And amazingly, for 2 qubits, this is not possible, but for 2 systems of size 3, 4, 5, and also 6, it is possible. So you see, this is imposing more constraints to get, in a sense, more extremal state, which is more useful for teleportation, for instance.
Yeah, I understand. Yeah. So no, my question was, instead of these AME states, if I define the maximally entangled states in the way I just mentioned, that you divide your parties into 2 groups, where at least one subgroup corresponds to having maximum possible entropy for that dimension. Okay.
But this is exactly what we did. We did it this exactly. We used this recipe under additional assumption that this has to hold for any splitting of the system into 2 parts. For any symmetric splitting of the system.
Okay.
So it is a good remark, but in a sense, this was exactly as we proceeded.
Yeah, because I had a discussion long time back with Anthony Sudbury, Sudbury and Higuchi, who did this 4-qubit case, where they have shown that AME does not exist for 4-qubit. So they mentioned this thing to be that this is anyway. Now this is, I think, a better clarification. Okay, thank you.
Thank you very much. And also, let me also thank for all of you who wrote me emails on the chat. Yes.
Okay. You can email. We are out of time. So thank you, Carol, for your nice talk. Thank you very much.
Thank you for the invitation to India. Thank you very much. See you again.
Okay.
Bye-bye.
Bye. So our next speaker is Ritobroto Sengupta from ISR Beharampur. He also loves mathematics very well, and he loves to do hard mathematics in physical problems in quantum information theory. So I invite Ritobroto for his talk. Okay.
Thank you, sir. May I just share my screen? Okay, please let me know whether you can see it properly or not. Am I visible?
Yes, it is visible.
Very good. Okay. So let us start. So first, I thank all the organizers for allowing me to talk in this occasion. And of course, I was initially a little bit, I was thinking that what exactly I should talk about. But then I recall that I am talking in front in Indian Statistical Institute, Calcutta, which has a nice and long connection with mathematics and statistics, of course. So I thought I would say something which is which is kind of quantum statistical in nature. So let me say that last couple of years, me and my co-authors are trying to generalize things in statistics or the stochastic processes in the quantum versions of those stochastic processes. In particular, we are studying the quantum stationary processes for Gaussian states. and we are trying to find out the properties, and at the later part we'll try to see that how we can use it for various other things. So here is the paper. This is a part of the long project, and the paper was titled as a zygotype theorem, distribution of symplectic eigenvalues and its applications for change of Gaussian states. This is in collaboration with, again, Professor Rajendra Bhatia and Tanvi Jain. Both of them are in ISI. Well, Professor Bhatia has been shifted to Ashoka right now. Okay. So without much delay, let me start because we don't have much time. So just a second, why it's not moving. Okay. So I want to first discuss what are the quantum processes. So in the celebrated little book on this foundation on the treatise of probability, theory of probability, Kolmogorov introduced a notion of a stochastic process as a consistent family of finite dimensional probability distributions in Rn, where this n is equal to 1, 2, 3, etc. And in the same spirit, a quantum process can be described as a consistent family of density operators, or equivalently states on the tensor product systems like H1, tensor H2, tensor etc. up to Hn, with the Hilbert spaces where n is 1, 2, 3, 4, etc. Now, this 1, 2, 3, 4, these are actually called as a time set, and just as a passing remark, which we are not going to emphasize for this talk, that one can replace it by any let us say abstract countable set with discrete topology, and that's topology also, and we can index those Hilbert spaces by using that. So like I can write, if you have these such an abstract countable set with discrete topology, then I can write it as, if any A is an element of D, then HA. And then I can write it as HA1 tensor, HA2 tensor, etc. in this form. And they will make a nice class of, a system of quantum, a collection of the quantum systems, and we can consider about the stochastic processes there itself. Of course, this is not classical stochastic process. I am rather bothered about the quantum stochastic process in it. So, and in this work, we are actually bothered about the special case when these Hilbert spaces are actually L2 of Rn for each and every H1, H2, etc. Or if you want HA1, HA2, etc. All these things. This n is the fixed positive number. It's called the number of in this number of modes of the process. And they have the Heisenberg computation relation, and from there we can do certain interesting things in terms of statistics. Well, but before that, let me just formally define the quantum processes. So a quantum system is in most elementary form will be determined by a pair of a Hilbert space and a state, where the Hilbert space is a complex separable Hilbert space and rho is the density operator. Okay, and that operator is the state of the system. So we shall deal with the several quantum systems and assume that all the Hilbert spaces in our work are complex and separable. And of course, the Hilbert spaces has a scalar product, the standard scalar, and which will assume without emphasizing much on that thing. Okay. Now, if I have a finite number of Hilbert spaces, H1, H2, tensor H2, etc., tensor Hn, then and we take a rho in a state on this joint system H, then we can write down the state as this big Hilbert space H, comma rho, and then I can take the marginal of that also. I just defined that. I just for completion I have given the definition, but we can just ignore that thing. We can just take a marginal, and the idea is that for the stationarity, the idea is that in a sense this marginals will be same if you take the same sized object marginals. Okay. Now I am interested in Gaussian states, as I said earlier, and the Gaussian states is very important for us to determine what are the thing which is called as covariance matrices. Now, covariance by definition is, let us say that if I have two observables x and y, then I can define the covariance of xy in a quantum covariance of xy in the formula given here. And if I have n observables x1, x2, xn, I can write down by using that the covariance matrix of it. Okay. Now, suppose I have a countably indexed set D, and and I have, based on that index set, I have a family of the Hilbert spaces, which we denote by SD, HA, which we denote by HA, where A belongs to D. Then I can take all of the set of all finite sequences of this space, or finite elements of this thing, that A1, A2, etc. An is in a row of A1, A2, An is a density operator in H of A1, A2, etc. An for each pair A1, A2, etc. N tuple actually. And if we have this nice property that they are permutationally invariant, number one, and number two, if I take a marginal, if I take the n+1 tuple and erase the last one, the n+1 to 1, then they are same for any such tuple you take, then we can call this the whole process as a quantum stochastic process over that countably indexed set D. If you are uncomfortable with this D, then you just consider D as the set of all natural numbers n. Now let us see what I want to do in terms of the Gaussian states. Just for a small recall, that if I take a Gaussian state in an n mode, and if I take the position and momentum operators in this way, that Q1, P1, Q2, P2, in this way, if we just group it, then the Gaussian state can be expressed by its Fourier transformation, which will be of this form, where L and M will be the means of the Gaussian states, and the S is the covariance matrix of it. Why I am bothered about this covariance, these Gaussian states, is that for Gaussian states, this is a very nice thing, is this covariance matrix. The whole concept of Heisenberg uncertainty principle, or which you can call it as the canonical commutation relation, which you call in mathematics, can be expressed in terms of this equation number 2. S plus I by 2 J2 is greater than equal to 0, where J2n is coming as 0, 1, minus 1, 0. In fact, from mathematical perspective, one can just start from this definition and then move forward, because this S contains most of the information about the Gaussian states. Like if you want to calculate the entropy of the Gaussian state, you have to see S, and you have to calculate the entanglement also, it will be reflected by S alone. Okay. I call this kind of matrices as the G matrix. So that is, for me, it is a 2n by 2n symmetric positive real matrix, which satisfies the equation number 2, actually, which we have written once again as equation number 4, that S plus I by 2 J2n is greater than equal to 0. There is a theorem which tells the following, that given such a given a Gaussian state, you can always find out a covariance matrix which is coming from here, which is actually obvious, but the converse is also true. If you are given a matrix 2n by 2n real symmetric matrix such that it satisfies this inequality, you can reconstruct a Gaussian state, mean zero Gaussian state. Mean you can put something else also, of course, mean zero Gaussian state with covariance matrices. Okay, so it's unique up to the covariance matrix, not up to the mean. Now, whatever we have told about the stationarity, it can be nicely reflected in terms of this this stochastic in this covariance matrices, because the whole matrix will be a block Toeplitz matrix, what we call as a block Toeplitz matrix, and we call this as a, because of the stationary nature, this block Toeplitz matrix should also satisfy the property that if you have an n by n blocks, if each block is of size 2n by 2n, okay, sorry, my bad, it is by 2k by 2k blocks, and if you take n by n these block matrices, then if you take any principal n by n block matrices, they will be same, actually. They will be same. So there is a stationarity with respect to time is coming out of that. So now my question is that, can we really characterize this kind of Gaussian states in this type of systems? Classically, we can do it. We didn't know so far whether we can do it in quantum way, and this whole work is actually up to find out what can we do. Okay, one simple example for such a situation is the case where which has a separate, which is the following, that you consider 2k by 2k blocks, and diagonal one you put it as A, 2k by 2k matrices A. The all upper diagonal parts put it as B blocks, and the lower diagonal parts you for the symmetry you put the B transpose. This is the most simple thing you can think right now, and this is what is called as the exchangeable chain. Actually, so it has some extra properties because all the diagonals of diagonals are the same. Okay. And but the next step is the stationarity, as you can understand, which is much more general. So in this case, you are going to get a 12-piece matrices where each of diagonals, the first, second, third, etc., the off diagonals are actually the constant blocks, but altogether it's not the same as. So exchangeability, as you can understand, is a very, very special kind of a stationarity. So what do you want to do? You want to find out the conditions on the block matrices such that the truncated chain at level n for each n belongs to n becomes a Gaussian state. Now this is the number one. The second question is that what is the entropy rate of such a chain? This is 2. This is a very, very difficult question. I'll explain it a little bit much later. But let me answer the question first, that for exchangeable states chains that we had a complete characterization now 7 years ago, and last year we got the general stationary chains. We couldn't do it, but just last 2 years ago we managed to find out, and the paper is this is the paper where we have published the general result. Just for simple feeling, let me just give one more specific case. Let us say that we have one diagonal thing that is A. The upper diagonal is again B, and the lower diagonal is also B. So you need to have again another level of symmetry. The B itself has to be symmetric such that B is equal to B transpose. And this can be, you can consider it in this way. The diagonal of the blocks are A. The uppers one are B. The lowers are B, but the rest of the things are actually 0. So I can try to find out what are the cases it may happen because I don't have much time. So maybe I can explain it, that when this kind of things becomes a stationary process. So suppose I have this 2 pairs of the cases A and B. So both are 2k by 2k real symmetric matrices, and it is necessary and sufficient the condition that this, if you truncate it at any level, it becomes a Gaussian covariance matrix, or in our notation as G matrix, provided A plus TB is a Gaussian matrix or G matrix for every T in the closed interval -2 to +2. So let us see the proof. So if I consider the proof is, the technicalities are somewhat just a bit, it's a little bit algebraic. So all I need to do is to write down this whole thing, the whole matrix which we have written here in terms of a nice block form actually, where these LJs are upper triangular matrices where J plus 1 upper diagonal entries are all equal to 1 and the rest of the things are zeros. Okay. You can take the spectral decomposition of that matrix. I'm sorry, there is a little typos. It should be it should be that bra and ket actually. And this lambda nr are the eigenvalues and this psi nr are the corresponding orthonormal basis for these eigenvectors. You see, if they are the eigenvectors, then I can write In also with respect to those eigenvectors, and they will not make much difference for us. Now, now one more observation is that each LJ is a matrix with operator norm equal to unity. So LJN plus LJN transpose as the operator norm not exceeding 2. Okay, and that means my eigenvalues lambda nr, this mod of lambda nr must be less than equal to 2 for each r. So that also gives me that I can write down, to check the Gaussianity at level n, I can write down this lambda AB plus I by 2 J2 Kn as the summation of A plus lambda nRB plus I times of J2K tensor of psi nr ket psi nr plus psi nr. That means we effectively managed to write this whole matrix in terms of a block diagonal matrices. Okay, and that what does it mean? But by that this thing is positive. That means that each block diagonal element has to be positive. That means each like A plus lambda nRB is a G matrix for each R. Okay, and now here we apply the theorem of Marduk and Szego. This is a very old theorem, and and it's a primitive version of that theorem. And using that, we can say, which tells the following: that if you consider the probability distribution, so consider the Dirac delta function where the mass is concentrated only at the eigenvalues, and then you take it as the uniform distribution of that. Then this Marduk-Szego theorem tells that this mu n, if you take the uniform distribution there, this uniform distribution converges weakly as n tends to infinity to the probability measure of L H inverse, where L is the Lebesgue measure in the unit interval. A little bit of calculation tells that your H is H of t is, it is basically coming from the Fourier series. It is equal to 2 cos 2 pi jt, and from there you can show that this t actually belongs to the interval -2 to +2. Okay, and that proves the necessity of the whole thing. The sufficiency also follows directly from there. I mean, this just reverse the whole process. Okay, so we could I can manage only to do here, and this is just for a small simple test case we proved it. But what happens if we have, let us say, n off diagonal, upper off diagonal elements and n or lower off diagonal elements? Along with that, if those, I don't expect any symmetry also, we have explicitly used the fact that B is symmetric here. So see, B is here, and B, I should have a B transpose, but B is symmetric, so B transpose is equal to B. So if we do those kind of properties, then what are we going to have? So we tried it very hard, and we noticed that, notice the following, that if I can, if I take this L infinity of 2k by 2k matrices, then they form with respect to a natural norm of essential supremum norm. This forms as a sister algebra. This block matrices forms a sister algebra, and the corresponding Fourier coefficients will be given by an of 1 by 2 pi a tilde of theta e to the power minus I n theta. The reason is that now that if we have the corresponding Fourier transformations, then I can write down the matrices. Conversely, if I have the Toeplitz matrices, I can get back my A tilde, which is giving me as the corresponding the Fourier transformation of which is giving me the Toeplitz corresponding Toeplitz matrices. Now, using it, I think Professor Sharkar, how much time do I have right now?
5 minutes more.
Hello.
5 minutes.
Okay. More. Okay, fine. So let me just hurry it up a little bit. So I can prove the following, that number one, that if I have, so the analog of this theorem, which we just now have proved, we can prove that if I have a stochastic process, given the stationary stochastic process which satisfies the Gaussianity, in that case, I must have the corresponding seed from where I am getting the block Toeplitz matrices, which I can call it as A tilde theta. This has to be also a Gaussian matrix for all theta there. Okay. Now, the second thing which is quite fascinating for us and which is very, very important for this information theory community as well as the stochastic community also, is to find out the entropy rate of this stationary processes. See, the whole concept of this stationary processes, working on this stationary process started mostly from the Second World War, when both in USA USA, it was Werner and Wiener, actually, Norbert Wiener, and in Soviet Union it was Kolmogorov who started checking that can we find out a nice way to predict certain stochastic processes in real time. So the result is was this kind of a study, rigorous study of this, what is called as the stationary the classical stationary processes. One very important thing is to figure out the entropy rate of these stationary processes, and the entropy rate can be defined in this following way. So you truncate the matrix at the level n, find out the entropy of that. Now, if n is increasing, then naturally this entropy will be increasing. So you divide it by n, and now it is kind of a normalized entropy. Then take the limit as n tends to infinity. Now this you can show that this is the proposition that you can show that in this case this limit exists. The limit may not exist actually, but in this case the limit exists, and this limit is difficult to compute. In fact, most often you will see in literatures that you are getting something like an upper bound or sometimes a lower bound, but you are not getting exact limit of the whole thing. So what we did is that for this to quantum stochastic things, we found out the exact entropy rate of the whole system. This came up by the following formula of again by which started from the Kak, Marduk, and Szego, and this type of results are now called as the Szego limit theorem, with a huge applications in not only in statistics but also in, let us say, the processes or the control theory as well. So we found out, unfortunately, till date, there was no version of this limit theorem, the Szego limit theorem, for the symplectic eigenvalues, which I need to find out to understand the entropy of any Gaussian state. So we found out for the in terms of the symplectic eigenvalues, and the theorem is the following: that if I take as nth level, if I truncate the block, and if I have a function which f, which is continuous in the interval of 0 to essential supremum norm of a tilde, then you take f of d, that is the symplectic eigenvalues, sum it up and divide it by n, and n tends to infinity. This is the same as you take the sum of all the eigenvalues of a tilde theta. Okay. A tilde theta, recall that a tilde theta's Fourier transformations are giving me the stochastic process, but it has to be for every theta. So I need to take an integration of that also d theta from minus pi to pi and normalize it by 1 by 2 pi. This is just from the Fourier series kind of thing, and the theorem tells us that this is our version of the Szego limit theorem, which tells us these two quantities are same. Using this, I don't want to go in the technicalities here, but using this, the thing is that if we have a stochastic process, then we have a single letter formula for finding the entropy of that. That is, you take the Gaussian the entropy of that SID, which I denote it by a tilde theta. Take the d theta, integrate it from minus pi to pi, and then normalize it by 2 pi. That is going to be the entropy rate of it. Just for our record, your S is actually given by the following formula: 2dj1 plus by 1 divided by 2 h of 2dj a plus minus 1 divided by 2j plus 1, where h is a Shannon entropy function to point the Shannon entropy functions. Okay, and h0 and h1 is equal to 0. So let us just summarize it. We found out an entropy for we have defined what are the quantum Gaussian stochastic stationary stochastic processes are. We showed that they exist, and we showed given the necessary and subsequent conditions of their existence. Then we have found out the entropy rate of that as well. And what I have not shown in this whole thing calculation is that we have also showed that the distribution of the symplectic eigenvalues, but that is a whole different level of computations, which I don't want to go right now. So thank you very much. And I should also thank my sponsors for supporting me, which are SCRB and DST. Okay. Thank you, sir.
Thank you. Any question? Short question. Is there, if not any question?
So maybe I can stop sharing.
Okay. Thank you, Ritupoto, again. Let's thank the speaker again for his 9 mathematical
I should
results
also
from
thank you,
quantum
sir.
stochastic process. This is a nice theorem. Okay. Thank you, Ritupoto. Okay, our next session starts at 16:40.
Can cross it thing.
Okay.
There is a cross, so.
Yes, maybe. Okay. My screen sharing is paused. Why is that?
Yeah, it is fine, but there is something color coming. Maybe you off first the
color.
Okay.
Yeah. Now you can see that these colors in the right hand side.
Yes. Wait a second. Now, of course, we have the.
Yeah.
Weird.
So
okay.
you can cross it. Yeah. Now it's perfect. I think.
Okay. So now.
Yeah. Yeah, there is a full screen. Yeah, enter full screen.
That's much better. Okay. Yes. Yeah. Do you see the?
No, actually, I cannot. It's not yet full screen.
No, it's not full screen. This is weird. Okay. Okay, maybe I just use the play. No, but then it's
the play usually works because this is Mac, right?
Yeah.
It's works.
But the thing is, I don't have the pointer anymore. This is weird.
Yeah, you have to make it then PDF.
That's a shame because I have 2 small animations, but okay.
Yeah.
Okay.
We can use the PDF. Yeah, do we still have a moment? Yeah.
Okay, our evening session now is to begin. Professor Aditi Hende.
Maybe we just use this one.
Chair this session. She got Bhatnagar Award a couple of years ago as a first woman scientist in the physical science domain. And she is also our good friend. So I invite Aditi to start the session. Okay.
Thank you. Thank you, Devashishda and organizers. So I am actually very happy to chair this session. There are three eminent speakers in this session. Professor Markus Huber. So Andreas will start this session. So Andreas Winter is an ICQIF professor at University Autonoma de Barcelona. And he did his PhD from Germany, I think University of Bielefeld.
Yes.
And today I realized that I know Andreas for last 15 years because I probably first met Andreas when we were in Singapore. And finally, we wrote a paper together. It was a very nice experience. After that, of course, I met several times in Barcelona whenever we visited Barcelona. So it's a great pleasure. So Andreas doesn't need any introduction in this community. So now, Andreas, your mic is.
Thank you very much. So okay, just to check, so you can see the screen because screen sharing is paused, which is weird. Okay, fantastic. Thank you for the nice introduction. Indeed, yeah, I also wanted to say that it's nice to be chaired by Aditi because we go back a long time, and of course, yeah, then we have this additional Barcelona connection, which is very nice. So yeah, let's hope we can realize some visits in person again in the future when things get a little bit easier. Yeah, so today I want to talk about two joint works I did. The first with these two guys on the left of the screen, Markus Grassl and Felix Huber. And the second one was only recently uploaded to arXiv. That was a research internship with Manideep Mamilapalli from IIT Kharagpur. And so, yeah, basically the title says it, we want to use entropy and its properties to say something non-trivial about error correcting code. And it's going to get progressively more complicated. So I will start with ordinary quantum error correcting codes, and we'll recall the so-called singleton bound for quantum error correcting codes. And then we're going to prove this it's a bound on the best performance of any kind of code. So we're going to actually prove a slightly stronger bound, namely the net entanglement production capability of so-called catalytic codes. And then we go to even more complicated things. So we get progressively more complicated, so-called entanglement-assisted quantum error correcting codes, and then finally entanglement-assisted hybrid codes that have entanglement, classical communication, and quantum communication at the same time. And so let's just start with a small reminder about what error correction is about. So there's this kind of very general theory of Knill and Laflamme. An error correcting code is basically an encoding of a k-dimensional quantum system into a bigger quantum system. So the smaller one is called a logical qubit.
Andreas.
Yes.
Sorry, have you changed the slide? Because I still see the first slide.
Oh, really?
Is it true for others also?
Yes, I have the same problem.
Yeah.
Okay, it's an issue with
Andreas, your slides are not moving.
Yes, I now understand. Okay, so we stop sharing, then we do it differently. Then I'll open a PDF. Then it's good that we have this. Sorry about this. Okay, so now where's my screen sharing? Apologies. Now this must be it. Okay, so this should be better. And now it should be moving, huh? Okay.
Yes, it is.
Sorry. So I didn't show much. I just showed the entropy, which everybody should know, the phenomenon entropy of a state. This is the outline. And so now this is the primer of error correcting codes. We want to encode in a bigger system, in physical qubits, a smaller system, and we want to be able to correct certain previously identified errors. So these errors are these error operators EJ. And so an error correcting code is basically, we can identify that with a subspace of the big space A with a projector P with these properties here, namely that if we're looking at all the pairwise products EJ dagger and EK of the error operators, if we compress that with the projection P on the subspace, this should be a scalar that only depends on J and K. And so this is a property that actually only depends on the span of these error operators, not on the actual particular choice. So it's a property of a linear subspace that is also called an operator system. And for the usual setting of error correcting codes, we have a composite system that is composed of n equal parts, each of them often a qubit, but I will look at larger dimension, q-dimensional system xi. And so the object of the usual quantum error correcting code is the so-called quantum Hamming graph, which is the span. So where the operator system, this linear space S here that I had here, is the span of all the tensor products of Pauli operators or generalized Pauli operators, where all but d-1 are identity. And so a code, which is a subspace of this x to the n n-partite system of dimension k, for this space of error operators is said to have minimum distance d. And it can correct errors of weight up to d-1/2 and so on. And so this is the notation that we usually use. We have the double brackets for quantum codes. N is the block length, K is the dimension, and D is the minimum distance. And we decorate it with a subscript Q to remind that it's not qubits, but it's Q-dimensional, so larger dimensional individual systems, which is important for this talk. And so the fundamental problem of coding theory is, for given alphabet size Q, block length N, and minimum distance D, what is the maximum K such that such an error correcting code exists? And so there's a long history going back to, well, the work of Shor, who invented quantum error correcting codes, to construct such things, but also to give bounds to basically say, okay, you cannot go beyond a set threshold. And so one of the most famous, one of the most basic bounds is the quantum singleton bound that says this, that the log of the dimension of this subspace, so the number of qubits I can encode, is upper bounded by n-2d plus 2 log q if d-1 is less than n over 2, so that this is in the bracket is positive, or less than or equal to 0, which means I cannot encode any qubits if d-1 is larger than n over 2. So this notation here, I don't think I will use it even that much, but it's sort of my private shorthand. This bracket subscript plus is the positive part. So if the inside is positive, then it's n-2d plus 2. If it's negative or 0, then it's 0. And of course, I need this log q because each individual system can carry up to log q qubits. And so it's one of the most fundamental bounds because in a certain sense, it's also tight. I mean, only in a certain sense, because, namely in the following: for every n and every d, if the alphabet size is sufficiently large, then there exists an error correcting code saturating the bound. So where log k is equal to the right-hand side. And those are called quantum minimum distance separable codes. In analogy to classical MDS codes. This is very important, this caveat for a sufficiently large Q. So for given alphabet size, there are additional bounds, of course, and well, as many of you probably know, even better than me, there are quantum Hamming bounds and linear programming bounds and so on. But if we are sort of abstracting from the alphabet size, this is somehow the most important bound. And so to show you how to derive these kind of things, I will just go through a little bit of quantum communication theory. So error correction ultimately has to do with channels. And so to talk about this, to make the connection with this Knill-Laflamme theory, it turns out that every so-called non-commutative graph, so every span, every subspace of operators that contains the identity and is closed under the dagger, arises in this way. It arises as a span of EJ dagger EK, where in addition the EJs are Krauss operators of a quantum channel, of a completely positive and trace-preserving map. So I can given this S, given this linear subspace of error operators I want to correct, I can construct a channel n of rho written like this in Krauss form, such that S is the span of EJ dagger EK, where J and K run over all the indices. And then encoding and decoding of an error correcting code, they are also CPTP maps. They're also channels. And so we can make a communication diagram that looks like this. So we want to transmit in quantum information via a noisy channel that we choose to be the one that I constructed just now. So we have our state in the logical qubits. There's an encoding that must be some physical operation that maps it to the n-partite system x1 to xn. Then the noise happens, which I'm going to specify later. And then we decode. There's another complicated CPTP map, but it's often described as an algorithm, as a circuit. And in fact, I can do that also here. Everything in the church of the larger Hilbert space, I can purify everything. All these maps I can write as unitaries with an auxiliary system, or more economically as an isometry with environment systems. For example, the channel has an environment E. And so an important step in the analysis is to realize that, well, if I am able to transmit the information, so if every state psi here in the subspace C comes out correctly at the end, then by linearity of quantum mechanics, I can actually preserve the maximal entanglement between C, that's my code, and the reference system R. So I only have to actually watch one state that comes out, that is put in here initially, and it comes out exactly in the same way. And so now if we abstract even more a little bit, and we're looking at this as a kind of an encoder circuit. So Alice is preparing this maximum entangled state and sending it through this isometry here. And then it just looks like this. So she's just from scratch creates a system R and all these other systems here that go into the channel. And so what that does is that it converts our error correction code into a scheme to generate entanglement between Alice and Bob, between the sender and the one who decodes here at the end of the day. And so the viewpoint of catalytic entanglement quantum error correcting code is essentially that Alice and Bob might start off already with some entanglement here, which in the previous picture they didn't. They just had nothing, and then at the end of the day they have some maximum entanglement. In the more general picture, they start off with some entanglement and they end up with some entanglement, and we're interested in what's the net entanglement production. And so if you can upper bound that, in particular, we upper bound the amount of quantum information you can send from Alice to Bob through this particular channel. And so, yeah, so to make progress from here and to go back to the singleton bounds, we need to abstract from this generic noise, which is just any channel. I mean, any channel I can write as an isometry from x1 through xn to x1 through xn with an environment here. We want these particular error correcting codes with minimum distance t. And so we need to look at the quantum Hamming graph. And its effect is very easy to see that this here is generated by an erasure channel that randomly erases d-1 of the n systems. So this is what the isometry does. It just basically partitions the n systems x1 through xn into one thing, x subscript I, which is basically the collection of all the x system with index I, and I has a subset, is a size of indices n minus d plus 1. And another part, xj, where j is the complementary subset of size d minus 1. And it tells to the receiver this set. So it gives a subset of n minus d plus 1 systems, and it also informs to the receiver of the channel, gives the other systems to the environment, and it also informs the receiver which subset it got, which indices it got. And so that means we can study now the error correcting codes in the usual sense with log length n and minimum distance d as properties of this particular erasure channel. So of course, here I drew just one realization. So this I is going to be a random set. We just assume that the channel uniformly randomly chooses one of those subsets of size n minus d plus 1. And so, yeah, so the communication diagram looks now like this. It's like the previous one with Trump, only that I inserted here now my particular erasure channel, where, so here I have my initial entanglement, here I have the encoding that is whatever. It's whatever because I want to prove ultimate bounds on what an error correcting code can do. And the decoding is also whatever, but it has to produce a pure entangled state here. And then I have the channel here that takes my n system and gives xi to the decoder and xj to the environment. And like I said, we're looking at the net entanglement production. So this kind of picture, I'm sorry, I'm moving a bit fast here in the beginning. This picture was introduced by Todd Bruin, Igor Devitak, and Min-Chu Xie a long time ago, both entanglement assisted and catalytic in quantum error correction. And so we're just specializing it here to the erasure channel to say something about the performance of a code. And so it turns out, okay, so let's go back here. The net entanglement production is, of course, a quantity that refers to the initial entanglement here, sorry, the final entanglement here, and the initial entanglement over here. But there's a nice trick looking at an intermediate time in the diagram. Look, I mean, this is a circuit where time flows from left to right on the screen. There is this initial intermediate time where there exists a sort of an instantaneous state psi, which we can use to express this. So the net entanglement production is actually the entanglement of A prime here, sorry, the entropy of A prime minus the entropy of B down here. So those two registers exist at the same time in the circuit or in the communication diagram. And so then what we prove in the paper with Marcus and Felix is this catalytic quantum singleton bound, which goes like this: the net entanglement production, which, remember, this is an upper bound on log k on the number of qubits I can send, because if I can send k qubits in any kind of error correcting code, I can use it to generate the same amount of entanglement, is upper bound by the positive part of n minus d 2d plus 2 times something we call sigma bar, which is this one here. This is the average entanglement, sorry, this is this is the average entropy of a block xj, averaged over all blocks, over all subsets j from this n of size d minus 1. And I normalize with d minus 1 because obviously this is an entropy of a d minus 1 partite system where each part has dimension q. So to get this sort of get this on a natural scale, I normalize with 1 over d minus 1 so that this is between 0 and log q. And so I can recover the original quantum singleton bound like this, because sigma bar is now upper bound by log q. So I mean, if you want, I just put this sigma bar to show that there is actually an entropic character that refers to the actual code, obviously, but we can learn something from this. Which I will show in a moment. I just want to show how do you actually prove this and where do these averages of entropies of sublogs come from. So when you look back at this state psi here, there we have systems xi, xj, a prime b, and this f, which is basically just a kind of it's the environment of the encoding, which often is trivial, but for maximum generality, I allow it. And so we have this by subadditivity. The entropy of xi plus the entropy of b is larger or equal than the entropy jointly of xi and b, if I just took it the joint state. Because the overall state is pure, I can go to the complementary registers. So because I only have these 5, the entropy must be the same by Schmidt decomposition if I go to a prime, f, and xj. And then I can split it up because I get this final entanglement that is pure, which means it's a product state with all the other registers. it means that this must be equal to the entropy of A prime plus the entropy of this fxj. So the f you can basically ignore. It oftentimes doesn't occur. It's just an annoyance in the proof. And then we have here the entropy of A prime plus the entropy of xj plus this residual bit. And so our inequality is this here now. The entropy difference, this is the net entanglement generation, is upper bound by, and this is true for any partition of the n systems into xi and xj, entropy of xi minus entropy of xj minus this annoyance. So I write it again here in yellow. Then we average, because what our channel does is it gives us a random xi and a random xj to the environment. So we average here over all subsets of size n minus d plus 1 for I and d minus 1 for j. And then we have to distinguish two cases, as is clear from this formula. This positive part is either the number itself or 0. If d minus 1 is larger than n over 2, so this right-hand side will be 0, then we can, basically using strong subadditivity repeatedly, we can show that the right-hand side is negative indeed. And so that makes sense. An erasure channel that loses half of the systems or more cannot actually generate entanglement. In fact, it also cannot increase the amount of entanglement between the sender and the receiver by essentially an extension of the no cloning argument. The case of d minus 1 less than n over 2 is the interesting one. That's when non-trivial error correcting codes exist. Then by strong subadditivity, we can show this relation here in purple. D minus 1 times the average entanglement over the I sets is less than n minus d plus 1 and the average entanglement over the j sets. And so this again follows from a repeated application of strong subadditivity. And I refer you to the paper with Felix and Marcus, where we retrace a little bit the history of this lemma that I also reproved at some point without knowing that it had been known already for a long time in some this and that special case. So for quantum MDS code, this sharper inequality with a sigma bar that comes out from the proof essentially, it shows something nice in addition, namely that for a quantum MDS code that saturates the inequality, the necessarily sigma bar must be equal to log q, and that means that for each subset, the reduced state xj on xj must be maximally mixed for all sets j of indices with size d minus 1. And so from this you can derive that they are so-called pure codes. These are very, very nice codes with additional properties. And again, I refer to the paper or to the expertise of Felix and Marcus, who study these things a bit more than me. Let's move on to the entanglement assisted code. Actually, since I lost a little bit of time in the beginning, I think I should speed up. So basically, we are complicating things again. So we are having this. We had this picture that our code is just there to to generate entanglement. But of course, that's not true. I mean, ultimately, we would like to communicate. And generating entanglement is not the same as communicating. I mean, for example, we might have already a lot of entanglement to start with. That doesn't mean that we can communicate. Obviously, entanglement alone doesn't allow us to communicate. It has to go through the channel. And so that we basically complicate our communication diagram. We put back this reference system in the code. This is the stuff that we would like to send. This has to come out here in C prime. We would like to reproduce the maximal entanglement here. And in addition, we also have initial and final entanglement. So this is entanglement assisted quantum error correction, also invented by Brun, Devitak, and Gier. And so if you are a bit lost here, let's look at this again with calm. This communication diagram is supposed to model that we want to transmit log k, this is written as small k qubits, with a reference system basically just there for bookkeeping. It's out of hand. Nobody, Alice or Bob, has access to it. And an entangled state that is shared between Alice and Bob here initially and also finally, so that we can talk about the net entanglement consumption now. Because now we think of the entanglement as a resource. We use the entanglement to facilitate the transmission of the C. We know this, that if Alice and Bob share entanglement, they can actually send more qubits in general for a noisy channel. And so again, we're looking at this intermediate time here just before the decoding to have a multipartite state on which we can study the properties of this error correcting code. And so I will spare you the details right now. The result we derived in the first paper is this: for any entanglement-assisted quantum error correcting code that's written like this: block length n, k is the number of qubits, d is the minimum distance, and L is the net entanglement consumption. It holds this here. There are two cases again. If d minus 1 is less than n over 2, then we have these two inequalities. And if d minus 1 is larger than n over 2, we have actually 3 inequalities. And so let's review them one by one. The first one comes from catalytic entanglement quantum error correcting code. This looks at k minus L. K minus L can be interpreted as a net entanglement production if I convert the k qubits I send into entanglement. And L, remember, is the entanglement cost, so minus L is the entanglement production. This is, you should probably just trust this kind of bookkeeping way of thinking like this. Resources, they work very much like a bank account. I mean, if you're in the positive, you have something. If you're in the negative, then the minus amount is what you owe. So we basically use this kind of thinking for the resources. K minus L can be interpreted as a net entanglement production. And we know that we have these upper bounds here from the previous round. We also have these two inequalities. They talk only about K, so L is not mentioned. So that means this inequality is true however large L is. Even when I have unlimited entanglement, K is upper bound by n minus d plus 1 times log Q. And this is basically this can be interpreted as a classical singleton bound, because with unlimited entanglement, a quantum erasure channel is equivalent to a classical erasure channel, but with a the square of the alphabet size. And then once I have a then I can use classical error correction to send classical information. I can again transform that into a quantum channel by teleportation using even more entanglement. And so these bounds, they basically follow from classical error correction. And then there's a last one, which looks really weird. And I mean, to be honest, we also thought of it as rather weird, and I would say we only understood it in the work I did recently with MoneyDeep, where this comes from, why we have this. So this brings me to the fourth part of the talk. We want to look at how tight these bounds are. So in the spirit of the classical and the quantum singleton bound, now we're applying the same reasoning to the entanglement assisted codes, where we're just looking at an erasure channel. The bound we get bounds, some bounds on the performance of entanglement assisted error correcting codes. And I would say, just by analogy, we would like to call codes saturating these bounds entanglement assisted quantum MDS codes. The question, of course, is, do they exist and what's their structure? So let's plot the regions we get in this by these two cases. Actually, we make three cases. We make d minus 1 strictly less than half, n over 2 equal to n over 2 and larger than n over 2. So delta here is the normalized relative distance, minimum distance. And so the regions look like this. And I just want to point out that they turn out to be identical to what you get if you study the Shannon theoretical rate region of entanglement versus quantum qubit rate of an erasure channel with erasure probability delta. This is very beautiful and the very important principle in this kind of analysis. So let's look at the d minus 1 less than n over 2. So this is the case where we know that quantum error correcting codes, even without entanglement assisted, exist. And for example, we know that there exists a code with n minus 2d plus 2 and minimum distance d if alphabet size is large enough. And so this takes care of this point QNDS here. And by turning qubits into entanglement, we can move along this line down further to the left. And also this point EAQ, the entanglement assisted quantum capacity in my language, this also corresponds to a known code. The parameters are n for the block length, n minus d plus 1 for the number of qubits, and d for the number of for the minimum distance. And so this also exists for, this also exists for all d less than or equal to n. So we can also go up here and then to also this line here and also the line to the right, the horizontal line. And so the reason why this is possible is because there is a kind of a propagation rule that allows us to turn a non-assisted quantum MDS code with parameters n, n minus 2, d plus 2, and d into an entanglement assisted code where we have L amount of entanglement, we have the same minimum distance, we have the same amount of information code, but we use fewer physical qubits. So we basically turn some physical qubits into pre-shared entanglement. And that's possible because we have an MDS code. I'm not going to go into it. Unfortunately, I will focus on the bounds. Let's look at the other regime when we have d minus 1 larger than over 2. So again, this EAQ point, we have that. This is this beautiful entanglement assisted code that sends the maximum amount of quantum information with using the minimum amount of entanglement. And the point MDS, this is a very curious one. This was elucidated by Markus Grassl in a previous work, actually. This comes from the existence of a classical MDS code with minimum distance d and n minus d plus 1 code length, if q is large enough. And what we do is we use it to transmit the classical information from teleporting qubits. And so if we can send n minus d plus 1 log q classical bits, we can send half of that number as qubits by teleportation using an equal amount of EPR pairs. And so that means we get this line with slope 1 here, with that point here right at the end where the kink is. And then we have this line, which is very mysterious. This comes from the third inequality that I showed before, that is these fractions that we didn't quite understand. And so let's see if I have time to show. So Aditi, sorry, I didn't watch the time. How much time do I have actually?
Hello. Yeah,
yes.
You have another 15 minutes. So 5:25
Okay,
Indian.
that should be fine. Sorry. I think I was rushing it too much because I thought I was a bit confused with the starting time. I think it was 10 past. Sorry, thank you. So when we go here, when we look at this here, I'm going to write this again on the slide, but I really have to show it on the diagram. We know that this line here corresponds to actual error correcting codes. We also have this horizontal line, which is kind of trivial. I mean, once you have an error correcting code that sends some amount of qubits and uses this amount of entanglement, you can of course also make another code that uses even more entanglement by just being wasteful with the resource. So this part of the boundary we don't know how to reach. And the reason for that is that the two coding strategies are very, very different. Here, we are doing something truly quantum. We are using entanglement to help encoding quantum bits. And here, we are actually using classical bits, and then we're just piggybacking on top of that teleportation. So this is a fully quantum strategy here, and this is essentially a classical strategy concatenated with teleportation. And so we have found it very difficult to understand how to interpolate between this. I mean, we conjecture that there are codes that somehow at least approach this line in some sense for a large n or d or something, or for a large alphabet size, but we can't prove it. And so this suggested to us, I mean, it's Manideep and me, that what we should do is we should really consider an even more general setting where we study entanglement-assisted codes, where we have both classical and quantum information to transmit. So we have E-bits, C-bits, and Q-bits. And so, okay, this was my animation of the exploding brain, so that we have to save for another day. The communication diagram becomes again a little bit more complicated. So I add this blue bit here. This is the classical message we can send, and it goes into the encoder. It also goes here through the channel and comes out here again. And so M, the log of M is the number of classical bits we can send. The log of K is the number of qubits we can send. And L is this entropy difference. This is the net consumption of entanglement. And so we have now three quantities to juggle. So our code bounds are bounds on those three numbers, K, L, and C, with respect to N and D. And so luckily there exists a bit of work in the Shannon theory on how to bound these three amounts of resource for a general channel. And so this comes from an old paper by Xie and Wilde, and it's explained very nicely in Wilde's monumental book on quantum information theory. We adapt, I mean, since we only want bounds, we just adapt a so-called converse proof for a specific channel, namely our erasure channel that erases d-1 out of n systems randomly. And we have zero error, so it's actually easier than the Shannon theoretical setting, where we allow some epsilon error, and then the epsilon goes to zero when the block length goes to infinity. We can actually we can do everything in the finite n regime very neatly. And the result is this here. If an entanglement-assisted hybrid classical quantum code exists with parameters n, d, so these are block length, minimum distance, k qubits, c bits, and l e bits, then we have these bounds here. We have c plus 2k is upper bound by something, k minus l is upper bound by something, and c plus k minus l is upper bound by something else. And there is this free parameter t, which is just a real number between 0 and log q. And so I leave it like that. I didn't try to manipulate the inequalities even more. You can actually eliminate t because it's a free parameter. You get more inequalities which are less informative, in my opinion, and it looks a bit like the previous theorem with these strange bounds. So I just want to make a couple of remarks about this. So I'm not going to go into the proof in the same way. I mean, I showed this one reasoning with the entropy inequalities. It's more or less the same. You're using very similar kind of reasonings that come from studying the properties of the initial and the final state and translating that into the entropies. We essentially can plug it directly into Wilde's Shannon theoretical converse bound. Then what you have to do is you have to, because it works directly on the block length n, then you have to work a little bit to get it back down to expressions that don't involve the full complexity of the block length n, the code in particular, but you can sort of reduce it to these three inequalities. So first remark, for c equals 0, so that means no classical communication, we do actually recover the previous bounds. So then basically we only have these two bounds here remaining. Well, no, actually it depends. It depends whether d-1 is larger or smaller than dn/2. Then you can which of the bounds remain. In fact, in the second regime, all three actually remain active, and you have to choose the t correctly. Anyway, so sorry, you can recover from these here the entanglement assisted quantum error correcting code single bounds. The second remark, again, we can make a relation to Shannon theory of IID erasure channel with erasure probability delta, which is, as before, the normalized minimum distance. If you divide everything here by n, all these three inequalities, you get rates. You get number of c-bit divided by n. So it's the rate of classical communication, the rate of quantum communication, the rate of entanglement over n. Those bounds are exactly those of an IID erasure channel with this erasure probability delta. And again, we also do that in the paper with Manili. And the remark 3 is we can actually understand this region now much better than the previous one. And that's precisely because of the occurrence of this free parameter t. So for a fixed t, if you fix t in this range, you just have three inequalities with three parameters, c, k, and l. And so this defines a simplicial cone with a certain apex where all three inequalities are an equality, and a cone dangling from this apex. So the apex for t is this one here. So this is the number of classical bits, this is the number of qubits, and this is the number of amount of entanglement we have. And the cone, so this is the apex, and then you add another cone which has apex 0 origin, and this is the same cone for all t. So this is a universal object, and it looks like this here. Gamma, kappa, and lambda, where gamma plus 2 kappa is less than or equal to 0, kappa minus lambda is less than or equal to 0, gamma plus kappa minus lambda is less than or equal to 0. And so these apexes, as you can see, they are on a line between A0 and A log Q, and they look like this here. A0, we have this number for the C bits and 0 qubits and 0 E bits. And A log Q, we have 0 C bits and we have this number of qubits and this number of E bits. And so this corresponds precisely to a classical MDS code. I mean, to reach these kind of parameters, you need a classical MDS code for an erasure channel. And this here is this EAQ codes that we've seen before. There's no classical communication, it's only qubits and E bits. And the line connecting them are exactly as we conjectured. This is about interpolating between fully classical MDS and fully quantum entanglement MDS code. So we can even understand more about this. So this S prime here, that's a simplicial cone, like I said. So it's in 3 dimensions, so it has 3 sides and also 3 extremal rays that kind of go down from the apex or up. I don't know, it depends on the orientation. The extremal rays are spanned by these lines here. They are the kind of, these are the edges. They call them TP, RC, and DC for the following reason. They correspond actually to protocols. These are the resource, this is the resource protocol balance of teleportation. Namely, you need 2 classical bits. You need 1 bit of entanglement to send 1 bit of quantum information. This is resource conversion. This is, you can consume 1 qubit that you send to create 1 E-bit between Alice and Bob. And this is transcoding. You can consume 1 qubit that you send, 1 bit of entanglement to send 2 classical bits. And so those extremal rays, they correspond to elementary protocols that we understand very well, which we can just concatenate with whatever error correcting code we have. And so this kind of looks like this. I just drew a very crude picture. So in this, if you try to imagine a 3-dimensional space, there is a point AT. If you can reach that one, so if AT is a set of K, C, and L in this 3-dimensional resource space, if there is a code that reaches this point, then we can, by concatenation with teleportation, transcoding, and resource conversion, we can get the entire cone ST, because we can move along these edges from the apex and also across those faces and in the interior of the cone. Sorry, I mean, forgive my drawing here. I was trying to give some kind of impression of a 3-dimensional cone, but I think it's in the drawing, it's not really that optimal. And so, yeah, so this is the end of the talk. So what you can learn from this, or what I had to learn, was that these singleton bounds, they really, I mean, that's sort of the unified way of thinking about singleton bounds in general, regardless whether you have only qubits, whether you have qubits and E-bits, or qubits, C-bits, and E-bits. So singleton bound is somehow what you get if you analyze an erasure channel. If you just derive bounds on your error correcting codes from how well they do over an erasure channel. And so this is indeed how you can think of how the classical singleton bound comes about too. It's just erasure channel. And in addition, you can do this by using plain Shannon theoretical entropic reasonings, which have the benefit of being actually robust against small errors. I mean, they are designed, the use of the entropy is designed that you get almost the same bounds if your error correcting code isn't perfect, but introduces a small amount of distortion in fidelity. And so what's remaining is the tightness of the bound. So we know that we can reach the point A0 because it's classical MDS code and the corresponding cone attached to it, S0. We can reach A log Q because that's the EAQ point of the fully quantum entanglement assisted error correcting code. And then again, we can reach the cone attached to it. And then all the rest of the region are basically translates of this cone because these ATs, they are on a line, on a straight line in 3-dimensional space. And this is the one we don't know. We're missing exactly again this line, classical MDS code A0 and fully quantum entanglement assisted MDS code EAQ. That's A log Q. And so this is a major open question, whether we can reach this line. But I think it's now much cleaner than the previous paper because now we really see that it's literally about interpolating between a classical and a quantum object. And so, yeah, with that, I thank you for your attention. Yeah.
Thank you, Andreas. Actually finishing exactly on time. So now it's the time for questions and comments.
Yeah, I think I blew everyone away. Sorry, I was a bit fast. I tried to cram too much into it, but I was very excited about the recent results with Manudip, so I didn't want to let go of it either. Read the second paper. I recommend read the second paper. I think it's much clearer than the first. Yeah.
Any questions or any questions from the YouTube? Can anyone tell if there is any question? Okay. Okay, so if not, let's thank Andreas once more.
Thanks to you. Okay, stop sharing.
Yeah. So,
yeah.
Hello.
Thanks. That's almost complete.
Yeah.
I mean,
okay.
I'm now also at the Technical University Vienna, and the ICQIF Vienna is actually from the Academy of Sciences and not from the university. But
okay. Okay, so I mean, I am sure that in this community, Marcus doesn't require any introduction. So now your turn to talk.
Yeah, thanks very much for this kind introduction, and and thanks to the organizers for putting together such a nice conference. I've been following a few talks. It's been quite intense with many great speakers and topics, and I realize it's been very, like, especially this session is very information theory, computing, math focused, and I'm sure you're all mentally quite exhausted. So I thought I'd take it a bit easier and talk about something a bit more conceptual today. So as you can see with my title slide, what I wanted to talk about is the connection of information to physics. So in all of these idealized quantum information protocols, like if you go and learn quantum information one-on-one from computing to communication, a lot of times you assume the possibility of preparing some initial pure state, right? I mean, you go and you start quantum computing, like before you start by drawing a circuit into which you input like perfect pure zero states, logical zero states. And indeed, our current capabilities of manipulating physical systems makes that, depending on the degree of freedom, a decent approximation. But of course, to get there, we kind of need to be able to create pure states. So, and there, I was often confused at the fundamental basics of what does it actually take to create a pure state within, within the laws of quantum mechanics, but most importantly, how do we actually do it in the lab? I mean, and then there is this kind of inescapable conclusion that once you take physics into account, you kind of, these pure states do not come for free. They're difficult to prepare. And there is a certain work cost, energy cost, entropy dissipation, heat dissipation associated to preparing this. And when thinking about it, and reading through the literature, you realize that what is actually required and how costly this is and what the fundamental limits are. For me, it depended a lot on the kind of a paper from which sub-community I'd opened. So like it depends a bit if you go from stochastic thermodynamics, classical thermodynamics, quantum information theory, and or open quantum systems, and like I was a bit dissatisfied because I actually wanted to understand like what are the limits to cooling, what does it take to prepare a pure state, and how can we even approach this problem. And that's why we got together in this kind of huge collaboration. You can see the photos of my friends and colleagues of this particular paper and some surrounding papers that I will mention that involve even more people that are now dispersed across different places and come from all over the world. So the title that we chose was Landauer versus Nernst. What is the true cost of cooling a quantum system? And the title, maybe for those who do not know what it refers to, there is of course a celebrated result, which is kind of goes back to Rolf Landauer, and it's the first to make that kind of connection between information theory and physics. And it loosely states that essentially to erase a completely mixed bit, it refers to a classical bit. So there is a certain like heat dissipation of erasure, which is essentially the Boltzmann constant times the temperature of the environment times log 2, i.e. the information content of a completely mixed bit. And that would seem to give a reasonable answer, right? Okay, so depending on my environment temperature of the lab, the amount of heat or entropy I have to dissipate is given by, or the work I need to spend. I mean, there's various formulations. It's roughly proportional to the temperature of the lab, the constant, and the entropy. But of course, if you follow this kind of theory of thermodynamics, then you have one formulation of the third law is called Nernst unattainability theorem, which tells you that to actually cool a finite temperature system to the ground state, infinite work or / infinite resources have to be expended. So it seems that within a finite universe, I will never be able to perfectly create a pure state. And at first sight, these two results seem to be a little bit at odds with each other, right? I mean, one of them tells you it's a finite and very small amount of heat I need to basically dissipate per state preparation step. The other tells me it's fundamentally impossible without expending an infinite amount of resources. And both of these, of course, come from the classical domain. So how does this even apply to quantum systems? What are the limitations? And which one of the two is true? And of course, well, to those that have actually studied the results and not just superficially read some papers as I initially did, you immediately come to the conclusion that the discrepancy is a bit of a fake one, because of course, the third law of thermodynamics remains true, and the Landau erasure cost is achieved only in a very asymptotic sense of infinitely slow processes. So it only costs you kT log 2 units of entropy to erase a bit if you're giving yourself infinite time to do so. But of course, in practice, we want to do something about finite time erasure. And there's countless papers about like finite time erasure processes, mostly in the classical domain, realizing that there's a certain trade-off between how long it takes you to cool and how close you get to the ground state. And maybe one of the first things I should mention here is one of the first thoughts that come into your mind if you read the quantum information book, which is kind of, well, if you think about measurement, often measurements are presented as means of preparation. So like very silly idea. Why don't we go to the textbook and take a projective measurement, i.e. we have an unknown quantum state, and then we kind of have a detector and kind of a meter, as it's often depicted, and then afterwards, after the measurement, like with some probabilities, I get certain outcomes, and after the measurement, the quantum state shall be in essentially so rho 1 would then be m1 rho m1 dagger divided by trace m1 rho m1 dagger, or in particular if it's a projective measurement, essentially like we can equate this with the state 1 1. So that would seem reasonable enough, right? I mean, so all I have to do is to prepare a pure quantum state is to measure it in advance. And that would be true if that process were something that I could actually do. So the main problem here is that the projection postulate is, of course, a bit of an idealization that can never be realized. I mean, like, on the one hand, we don't have access to many actual non-demolition measurements where upon measuring the quantum system, the quantum system that I wanted to measure actually remains in place, right? I mean, think about photon detectors. They mostly absorb the photon and use it to trigger an internal cascade, and that photon is never released in its state again. There are examples of non-demolition measurements, but of course, all of them, they're not perfect. You don't have fidelity 1, you don't have the efficiency of 1, and so on and so forth. And there is a good reason for this. This is fundamentally impossible. Like the way we write down projections in a textbook is, of course, an idealization that is actually quite far from being realized. As a side note, there is this paper we once wrote about this, where we basically link the project, or any POVM actually, linked to resource expenditures or to the third law. I mean, it's kind of obvious when you think about it, but in essence, even like no matter what kind of formulation of the measurement problem you subscribe to, let's leave this aside for now. Let's just talk about a pre-measurement and suppose that in order to measure a physical system, I need to make it interact with a physical apparatus that is my measurement apparatus. How the chain of quantum to classical then proceeds, whether things collapse, whether there are many worlds, or the things there's an objective kind of collapse, or some Bayesian reinterpretation, whatever. In the end, what it matters is I will need a physical device to interact with my system. And if my physical device is not in a pure state, it cannot correlate itself with the system perfectly. So in order to implement the perfect measurement according to textbooks, I already need to basically violate the third law of thermodynamics, or turning it around, essentially the third law tells me how many resources I need to spend in order to even get close to what could be considered a projective measurement. Okay, so this was a paper written some time ago with Yelena Goyanova and Nikolai Fries, which was published in Quantum. And it's a bit of a precursor also to the subsequent investigations here. So I've been, like, we've been vague here in the title with the resource costs, and I've been kind of using dissipated heat, entropy, work, expenditure, and all of the time a bit interchangeably. And there's a good reason for this. Because we wanted to find out, okay, what is the true cost of cooling a quantum system? And level 1 answer, well, measurement isn't an answer, because if I can measure perfectly, I already can cool perfectly, and then I'm just running into tautology. So yeah, that doesn't give me an answer. So even if I want to understand what it takes to prepare a state via measurements, I need to understand what it takes to prepare a state via, well, what exactly is a good framework here? And even here, the literature will change drastically depending on what kind of assumptions you make on the interaction of the system in question and its environment. So one of the universal assumptions that you can make that is actually quite good is, so assumption 1, that the environment is in what we call a thermal state, tau of beta, where I'm going to be explicit. So the thermal state is e to the minus beta h over z, where these things have different names. Beta is the inverse temperature, it's 1 over kBt. H is the Hamiltonian of the system, and Z we call the partition function. And this is a uniquely, or not uniquely, this is an immensely interesting insight into physics, because it's very interesting to ask, how does the thermal state even emerge? But by now we know that even if I assume that the environment in some purification, so yeah, like to some extent, I mean, even if you're kind of a believer in the church of the larger Hilbert space and say, okay, at some point, at some level, surely your system can be purified, then yes, that may be, yet the effective description of any large and complex environment will still be the Gibbs ensemble. And there are various reasons for this. In fact, this is an entire research field. So here, there are many ways you can go about this. You could talk about the eigenstate thermalization hypothesis, which basically posits this happens on the level of individual eigenstates. You can talk about dynamical equilibration, where indeed this will feature a non-trivial time evolution, which essentially means that the time averaged state will spend most of its time very close to this thermal equilibrium state. Or you think about entanglement that is inevitably generated by interacting Hamiltonians, meaning that subsystems and with them local observables, which are more natural to us, will anyway essentially look thermal, even though the global state isn't due to entanglement. But no matter how you do it, this is the first assumption we take, and it's a very reasonable one, because at the same time, while we now have a good theoretical understanding of how this emerges, it's an observation that we actually that originates from empirical facts. So if we try to assign a reasonable state to a large and complex system, we can do very little without actually measuring details. And the best statistical description of that big and large state will come from assuming it to be in a thermal state, which can be more rigorously kind of argued through what is called Chain's principle. But in any case, that's assumption number 1. Okay, so that gives us a good start. So now we know that essentially we have a system, rho S, and maybe we have, like, I'm going to draw circuits like many of the speakers before did, and we have an environment. And the environment kind of needs, it's really, really large and complex, and we have no control over it. I mean, that's what essentially calling it an environment means. And with this, okay, so we realize it's a thing about control. So the assumption here is the environment is something I cannot control. The system is something that I can control. And if that's the end of the story, there's very little I can do, because if I can just act on the system and not act on the environment, then essentially all I can do is at best unitary transformations of my system, and I cannot change the entropy. So we need to go a bit further than just saying I have no control over the environment, because I need to somehow interact with the environment in a controlled way. And to do this, we're going to introduce a mediator, which we call machine, such that essentially I can have controlled interactions between my machine and my system. So here I can essentially induce a hopefully close to unitary interaction, and the machine in and of itself can essentially thermalize. It can interact with the environment in an uncontrolled way and reheat and rethermalize. So that seems to be a reasonable paradigm. So like if you want to think about it, it's kind of just a CP-TPT map which traces and replaces the state of the machine with the thermal state of the machine. Or we can model it physically by some time-dependent interaction in some open quantum system dynamics and see that it basically closely approaches the thermal state by uncontrolled interaction with a large environment. Okay, but that now gives us a little bit of a framework to talk about how cooling could work. And indeed, so I will not write down the full references, but you can ask me about any of them. Like all this equilibration, there's, I think the most recent review I'm aware of is by Christian Gogolin and Jens Eisert, which gives us a very good overview. And here I should mention there's a seminal paper that focuses on in this paradigm on the cooling cost, and it's by David Reb and Michael Wolf, and it's called Improving Landau's Principle. And so what do they prove? They prove that in this paradigm, beta EM, where E is the delta EM, I should say, the energy change of the machine part is going to be equal to delta S of the system plus the mutual information of system with machine plus the relative entropy of the machine state after the unitary and the machine state before the unitary. And that is if U is unconstrained. So you see, so if I really, if I have no limitation on the type of interaction I can induce between my system and the part of the environment which I might call machine, then this equality holds. So the inverse temperature times the energy change of the machine is equal to the entropy change of the system. And you see these two terms, the mutual information and the relative entropy, they're positive, semi-definite. And at best, they could be zero in the limit where there are no correlations created via this unitary between machine and system, and the change of state is basically negligible. So if this goes to zero and this goes to zero, well, then what we get is delta EM is equal to KBT delta SS. And that's kind of what we remember about Landauer's classical result. It's just that it's rigorous for quantum systems. And you can see that in order to approach it, I need to find a unitary that acts between system and machine in such a way that it creates no mutual information and doesn't change the state's entropy of the machine. Which is, of course, impossible unless that machine part is of an infinite size. And so this unitary basically needs to connect an infinite number of qubits, for instance. But it kind of tells you that that Landauer's bound is indeed achievable in the quantum realm if you have perfectly unconstrained unitaries, but you really need to control an infinite size environment. And that's the thing, right? I mean, we wouldn't call it environment if we had a perfect control over it. So usually we just have a control over a very small part, and that kind of precludes the achievability, but at least we can kind of gauge what the corrections are, right? I mean, so what, we cannot cool at the Landauer limit, but we can maybe cool perfectly by at least allowing for some relative entropy and some mutual information. Well, unfortunately, not even that is true, right? Simply because there is another formulation that makes at least the asymptotic version of the third law of thermodynamics entirely obvious, right? So if you think about it, what I'm really thinking about is a unitary that acts on rho system, tensor rho machine, where this here is supposed to be a thermal state tau of beta, U dagger, and then I'm taking the trace over the machine part, and that's going to give me my rho S prime. And if I'm thinking about this, well, if this here is a full rank matrix, which the thermal state always is, and this here is a full rank matrix, then of course it follows from these two facts that rho SM is full rank, which means that the unitary transform is also full rank, which means that the partial trace of it is also full rank, which means that I cannot reduce the rank of my target system. It's a simple entropy inequality. And therefore, no such operation on a finite rho M can give me a pure output state, not even if I allow for correlations or the relative entropy to change. So, okay, this was a really nice and quantum information inspired paper, but then let's think about what it even takes to get there. I mean, well, of course, yeah, I need control over an infinite environment. I need basically to do unitaries that do something very strange. But I need something more. I mean, if I think about it from a thermodynamic point of view, unconstrained U basically means the entire unitary orbit. And that's problematic for two potential reasons. One reason I'll get into later is complexity. But another reason that if you open any kind of paper on the so-called resource theory of thermodynamics is the fact that this is not a very self-contained description, right? I mean, the unitaries of any autonomous system that does not require any time-dependent control is essentially given by e to the I ht, where h is the Hamiltonian of the system. And that in and of itself commutes with h and thus cannot change the energy of the system. So unitaries to change the energy of the system aren't very natural evolutions of closed quantum systems, but they're good approximations. But then I need kind of a time-dependent classical control, and that hides resources. So that's why we basically classified, we wanted to generalize this kind of setup into frameworks that can be rigorously treated and compared, and make explicit note of what resources are assumed to be controlled. And we call this kind of the coherent and incoherent paradigm. Here is a little comic that's Manu Schwarzhans, one of our authors, draw. He draws much better than I do, so I spare it. And now let's think about it again. Here's the circuit diagram that I first explained to you. Here I have a system and a machine, and I have an experimenter who uses some amount of work, some classical time-dependent control to induce a unitary. But if I go back and think about it, I also want to be able to maybe do multiple cycles, because yeah, maybe I cannot do it in one cycle because I can only interact with two parts of the environment in one go, but maybe these two parts of the environment can then be rethermalized at least. This is why we switched all the protocols into a control step and into a rethermalization step, where afterwards I essentially can have the machine be coupled to the rest of the environment in a very uncontrolled fashion, and thereby triggering a release of heat or an intake of heat, whatever the final state is, effectively rethermalizing the machine, and a repeat. So to do this, I need to be able to turn on and off interactions, and I need to be able to have a time-dependent control of interactions in order to make the unitary that induce energy changing. So this is kind of the paradigm in which Reeb and Wolf work. And if I want to also include a reformalization step, then this is what is also known as algorithmic cooling, which is basically an algorithmic approach where I essentially also draw a circuit diagram with fixed energy gap ancillary qubits that I'm allowed to reformalize, and arbitrary unitaries I'm allowed to perform like a quantum computation, and I essentially can cool via computation. Okay, but it only covers part of the theory, and it assumes a large amount of control, which sometimes may be justified, but of course, in terms of serving for fundamental limits, is a bit dissatisfying, because of course, I might be hiding even more resources in the classical control step. So that's why we also think about what we call incoherent control, where the experimenter is reduced to essentially turning off and on interactions between system and machine and environment. And that's it. No detailed time-dependent control of internal degrees of freedom necessary. So here we just let the system run its natural course once an interaction Hamiltonian is turned on. And then we let it reformalize. However, here we need to add something, because that would essentially trivialize everything. No cooling would be possible if there's just a single environment. Here I need a source of work. And before, the source of work was the experimenter supplying work by essentially having time-dependent classical fields which induce time-dependent Hamiltonians, which induce an energy change. Here there is no such source of work, because the unitary is entirely self-contained and autonomous, as we call it. And in order to have some non-trivial work supplied to the system, the environment needs to be split in two parts. There is the room temperature environment, and I need to have access to something out of equilibrium, which in our case is a hot bath thermal environment. It's essentially the minimal environment that is necessary to non-trivialize the thing. Of course, I could have other non-equilibrium resources like some entropic battery, some weird out of equilibrium system. But of course, each of them requires extra experimental capabilities to prepare. So it's kind of the most basic resources needed. And if I do not constrain the unitary any further, and if I not constrain the size of the access to the environment, then this incoherent paradigm is also known as the resource theory of thermodynamics. And in the resource theory of thermodynamics, it's again, it's this map. So the partial trace over the system tensorized with a thermal state, unitarily evolved and tracing out the machine. However, in the resource theory of thermodynamics, U is assumed to commute with the Hamiltonian of S plus M, i.e. it's supposed to not change the global energy and therefore be self-contained energetically for a better bookkeeping. The way we deviate in our paper from the resource theory of thermodynamics is to essentially limit the size of the machine. Why? Well, it's because we wanted to understand the specific interplay with complexity, something I will now get to, by a simple, very stupid example, but that should nonetheless illustrate all the complicated theorems and proofs that we have set out in this paper, because you can imagine how you would try to generalize those. So let's think about it explicitly. How would I algorithmically, via interaction with a machine, essentially cool at the Landauer limit? And it's very instructive to think about how some of the early descriptions of a quantum Landau ratio looked. So I have a system with a Hamiltonian, like here E times 1, 1, like where E is the energy gap between the two, and here is the ground state. Without loss of generality, I set the ground state of the qubit to 0. How would I Landau erase this? Well, I would essentially infinitely slowly raise the energy. So the energy would basically go larger and larger and larger, continuously thermalizing with a thermal environment. And you can imagine, like, I raise it ever so slightly, but then the thermal state has a slightly lower excited state population, right? Because if I write the thermal state of a qubit, it's really just 1 over z, 1 e to the minus beta e. And so here you can see that by increasing the energy gap E, the natural thermal state essentially is an exponentially small excited state probability. So what do? I slowly and adiabatically raise the top level, continuously dissipating heat along the way. And then I essentially integrate all the heat that's dissipated until it reaches the top, until it reaches infinity, because at E at infinity, the top level population is actually 0. And then I quench down, but quenching down doesn't do anything anymore because there's no population. So I'm essentially changing I'm changing the Hamiltonian of a subspace that is not populated, which comes virtually at no cost. Okay, so what would a quantum information or circuit version of this be? Well, I could just think about it this way, right? I have a system, and then I have a machine with a slightly higher energy gap, and then I do a swap gate between them. What would this do? Well, it would exchange my excited state population for the thermal population of a slightly more energetic machine qubit. And to do so, it'll cost me some energy, but it'll make me a little bit colder. Well, what do I do next? Well, I do it again, but I do it this time with an even more energetic one. Again, a swap. And I do a whole chain of these, and I do a ladder, and ever so slightly, I keep increasing the energy gap, and I keep doing swaps. And now this is a nice finite time, finite version, finite everything protocol, and you can see what happens. So if essentially the delta between the steps, if this delta goes to 0, and the energy gap of the nth qubit goes to infinity, which basically implies n goes to infinity, then I compute the energy cost of all of these swaps. Well, surprise, it's going to be kT delta S. So here, this is an explicit circuit version of Landauer where you see the infinities coming in. Okay, what else could I do? Well, I could just make one swap with a gigantic qubit with a huge energy gap, just a single swap gate. And what I do here is the energy cost, so this is kind of delta E, sorry, and here delta E goes to infinity. But here, the time it takes, T, essentially goes to infinity. There's an infinite number of swap gates I need to consecutively do. But here, the time is finite. Well, or 1, whatever it takes you to implement one swap gate, but implementing it by e to the IHT basically takes a finite amount of time. Okay, and yeah, so, okay, and then another very stupid idea. Okay, so I can cool with infinite energy and finite time, or infinite time but finite energy, and I can interpolate between the two in the finite regime and can basically compute a little bit of a trade-off. But wait a second, what if I'm just being silly and I just write the total U of the protocol up here, the total U, I can write as like un minus 1, yada yada, U1, right? It's a product. And it's a new unitary that I could see induced, like where each of these basically is induced by a Hamiltonian that induces the swap gate and some finite time that it runs for tau. Well, I could just find a new Hamiltonian, e to the minus I h total, and then some tau prime. And then essentially I can do with a finite time and a finite energy perfect cooling. That's nice. I mean, one could say that technically, yes, this is possible. And yes, technically, not even the Hamiltonian itself diverges more than the Hamiltonians that would in the other proofs. But so what's the catch? Well, the catch is what we are trying to find out. So the obvious catch is if you look at this Qkd protocol and you look at the Hamiltonian, you look here, that Hamiltonian has an infinite interaction range. And we know nature just doesn't provide us with those. Like with quantum computing, most naturally, two-body interactions would be at the basis of all of these interactions. So actually this circuit, like if I draw it as a circuit, I mean, it would be, right, it would be, I interact with this one, and then I interact with the next one, and so on and so forth, right? So this kind of circuit is a natural circuit also in terms of complexity, and it has a complexity of n, like a circuit complexity of n. And here I can do it in one step, but this is essentially by expanding my gate set to have infinite interaction range Hamiltonians, which just aren't physical. So in some sense, you could say it's complexity of the generating Hamiltonian that is infinite and time and energy that is finite. So that's why we call this kind of a triangular relation, right? So what you can do for perfect cooling is an infinite complexity, infinite time, or infinite energy. These are the three resources. And of course, in the asymptotic limit, this seems like a bit of a silly example, but it's actually not so trivial to find out once you go beyond qubits, once you have actual qubit computers, maybe continuous variable where everything is infinite from the start. Here, local is actually fine, but then you suddenly have infinite polynomial degree of the generating creation and annihilation operators, so infinitely non-Gaussian. So depending on the physics, that complexity could mean something different, and we're yet to find something that really universally binds it together. But roughly speaking, this is the kind of trinity of cooling that we have. And that is, I can cool perfectly given infinite energy, infinite time, or infinite control complexity. And the more interesting case is, of course, the finite case where I can trade these off, right? I mean, okay, if I'm allowed to take twice as long, I can cool with half the energy or half the complexity, and then try, like we have some examples, figuring out all of these relations. But that is all within this kind of paradigm of full control in this coherent control paradigm, which is essentially the paradigm that most quantum computers work in, because in quantum computing, we anyway assume that we're able to do any unitary. The only thing that is really the constraint is complexity, like we have to decompose it in terms of some universal gate set, where the basic entangling gate is usually a two-body gate for very good physical reasons. But how does this then pertain to the resource theory of thermodynamics? Well, the good news is that you can actually generalize Landauer's bound to the incoherent case, to the resource theory of thermodynamics too. Essentially, you will find a very similar triangle. So if I'm just going to write the inequality now, which we call Carnot-Landauer bound. So it's the free energy change at environment temperature beta of the system plus the Carnot efficiency of the process times the energy change of the hot bath is upper bounded by 0. Now, this might look odd at first, but trust me, for time reasons, that if you let TH go to infinity and with it the Carnot efficiency to 1, then you recover the usual Landauer's bound, or the improved quantum Landauer bound by Riemann-Wolf. But there is a slight caveat I should mention with respect to this result, because interestingly, here, essentially, as long as in the coherent control case, it's sufficient for one of those to diverge, and then I get finite other. But even at an infinite energy cost, I cannot cool. Even at infinite complexity, I cannot cool at finite energy and finite time in the Carnot-Landauer case. And that is maybe an interesting deviation. So there is something that can be gained from essentially that additional control, and we're actually hiding a lot of assumptions that in both of these cases are still not for free. I mean, I've now been pretending that this is then maybe the most autonomous case. Well, not really, because there's still some hidden assumptions. It's about how do we turn off and on these interactions. I kind of assumes perfect timing and the perfect control of the interaction Hamiltonian. And also this is unrealistic. And we've even written some further papers maybe about the thermodynamic cost of precisely timing devices. There are things known in the community as called thermodynamic uncertainty relations. So even the bottom one, even with a finite size environment and a finite size machine, is an idealization that we can only aspire to get close. And maybe that little glimpse into quantum thermodynamics gave you some idea why we're so many orders of magnitude away from even coming close to Landauer's bound, especially in the quantum machine. And I hope I've convinced you that maybe it's a good idea to try and get a fundamental understanding of these limitations, because creating pure states is a pretty important task in almost all quantum technologies. And with that, I want to leave some tiny space for questions. Sorry.
Yeah, thank you, Marcus, for a nice talk. So now it's time for questions. Yeah, I have one question. Yeah, actually, you have already mentioned. So the protocol that you mentioned of this swap gate for qubits, how you will actually you have a machine and then you will swap you will scale the thing. I was just thinking, because recently also we were working also on how we can generalize the thermal machines in higher dimensions. So even for qubits, this will be, I mean, the simple generalizations will be difficult. At least I cannot see, even if it is have 3 levels, for example.
Yes, absolutely. I mean, like, there are different ways you can do it. I mean, you can work in this kind of idea of using virtual qubits, something that was championed by Ralph Silver and Nicolas Brunner and Esco and so on. And but of course, that's basically working on qubits with a qubit environment, which might be a bit stupid. So then, but once the Hamiltonians don't match up, it's not even clear whether swap is a good idea, because
Another small just comment about this, the H total that you wrote. So I was just thinking that, I mean, suppose, I mean, you have a Hamiltonian which are, because, you know, in ion trapped, you can create a Hamiltonian with long. Hello? Hello, I was frozen or something, or I don't know.
Yes, you were frozen or I was frozen, I don't know.
Yeah, okay, whatever. So, so have you heard my comment or?
Yes. I've just switched devices because I thought maybe it's my device. Sorry, now I've lost track. In eintraps, you can create long-range interactions, and then?
No, I was just thinking that if you, I mean, in case of long range, but with a power law kind of decay, but then how this complexity scales. I mean, I still believe that it will be like, you know, what you also, I mean, kind of infinite in some sense, but so.
Yeah.
But I don't know, but probably serve the purpose of that kind of, you know, mimicking the swap gate, right? That was the main idea, right?
Exactly. Very correct indeed. So indeed, it's a very insightful comment. I think we've been thinking about this. So like a lot of systems might have longer range interactions, and actually harnessing them could, well, asymptotically it still will be infinite, but still,
yeah,
you can basically you can severely cut down the energy cost or improve the how well you approximate the pure state. Exactly. So there's a lot of improvements to be had. However, like in quantum computing, it's very hard to figure out how to use it optimally, because it's not just any long-range interaction Hamiltonian, but it's like a very specific one. So
yeah. No, I agree with that. But what I know that in the asymptotic case, it will go to infinity, but how it reaches the, you know.
That's very relevant indeed. And it's exactly what we're trying to do now. Like, this is not in the paper yet, but this is the question we're trying to solve, and I cannot yet give you the answer.
No, okay. I just wanted to ask that whether you have any comment to make. Okay, good. I will look. Any other questions, comments? Okay, so if not, let's thank Marcus again and all the speakers in this session. So thank you very much.
Thanks a lot for your attention.
And back to the organizers. Devashish, I cannot hear you.
Thank you, Aditi, for chairing the session. Thank you very much for all the speakers of this session. Thank you all. We will meet tomorrow again at 11 a.m. Okay. Thank you.
Thank you.
তুমি একটু দেবে? আচ্ছা